Okay, so it's day 3, the final day of UCLA QC Bio Library Workshop 1B, UNIX Command Line II for spring 2024. So where we left off was, so I updated the slides again, so grab another, a fresh copy off of the link. So first, from your question yesterday, I did kind of poke around to see if I could give you kind of a good page to point you at. So Stack Overflow is kind of full of discussions about this topic, and this one in particular has like 44 answers, and you'll see quite a diversity of answers there, depending on like how fancy you want to get and so on, and like how portable it needs to be and so on. So you can look at that if you're kind of interested. One solution in there that kind of maybe is kind of the one I would pick out from there is to actually use a code generator. So like this argbash is one of them. And what this is it's a script generating script essentially. So you actually add comment lines to the top of your script that follow a certain format. It's like a mini language that you describe the options that you want your script to take. And then you let this thing play with it. And this thing will then turn those comment lines into shell code. Like all that stuff is basically stuff it generated. This is sort of the meat of the script down here. And it basically those are just settings. It just sets a whole bunch of shell variables that reflect what the command line options said. So the reason I pointed to this one is because it's actually pretty full featured. I think it covers pretty much all the cases, and I think the code it generates is pretty portable. So anyway, and unlike many of the other options, this little mini language it has is sort of non-redundant, meaning that you only mention each relevant piece of information once, whereas a lot of the other options you kind of have to repeat yourself a few times, which makes maintaining it and so on more difficult. So anyway, you can take a look at that if you're interested, but it is kind of a more advanced topic. So I also include on this page a couple like links if you're like want more reference material or stuff for shell related stuff. So one is this just like 1-page cheat sheet, which just kind of is just got kind of all the major different syntaxes just kind of here. It's not like really an explanation. It's just like, you want something, but you can't quite remember how to do it. And then you can kind of glance at this and you can kind of pick it up again. And there's more features on here than we covered, but there's actually like if else, end if kind of things in shell and stuff. And anyway, this little cheat sheet you can look through. It's so short that it doesn't take long to look through. These awesome bash, awesome shell, there's like these on GitHub. There's like people that like for pretty much every topic, they like try to collect like kind of like a curated list of web links and stuff. So like this awesome bash is basically just a list of all kinds of links to other resources. And awesome shell is the shell, like the bash page is bashish, but the shell page is just general shells. So you can look through those if you're interested. Another one you can maybe look at is Google's own shell coding style guide. So that is actually Google's document to their own software guys when they write shell scripts and stuff. This sort of kind of talks about like more of the style questions of like, well, yeah, you could do it this way or this way or this way, but we like this way because this reason and stuff. So, I wouldn't read that first, but that's Google's own internal shell style guide. And I think this is actually also associated. This next one is associated to Google. The shell check is. Did I give you an example? Yeah. Okay. So, yeah. So you can paste in your script to shell check, and then it just gives you advice, right? It sort of like looks at it and it sort of knows what common mistakes are and stuff and whatever. And it may not be correct, but it sort of gives you like hints that says like, oh, I don't think, these lines you really ought to think about because it's like, I don't know. So like, that's sort of what we call it, like a linter. It's just kind of like a problem checker. And the last one here is the Advanced Bash Scripting Guide, which has been around a long time and it has lots of sections. And if you're interested in particular, shell functions or something, then it has like a page that kind of talks about those with sort of, it may not assume that you're like doing this the first time, but it's going to talk about kind of more, like little gotchas and stuff and FAQ type stuff and so on. So anyway, yeah, so those links are there on this new slide that if you go to and grab a new copy of the slides, there's this slide now in there. Okay, so yeah, so let's get back on Hoffman. Oh, and before I forget about the homework and the quiz. So those of you that are taking the course for credit, there is a short quiz, like 10 questions, multiple choice. I'll send those out by like Monday, and then you have a week. So, you know, we're almost at the end of this week, and then Monday is just after the week, and then it's the Monday after that they come back. And just email me back, you know, you can just, if your answers are A, B, C, D, E or whatever, you just send me an email A, B, C, D, E, right? You don't have to be fancy, just make the subject line do something like work W1b quiz or something. So it's easy for me to find out of the junk. Sometimes they go to the junk mail folder. So, and the homework maybe should take you like an hour or two. But that's more like a written, that's like you're going to do something on Hoffman, right? And then you're going to like take screenshots or copy and paste text into like a Word document or a Google Doc or something and send me like a PDF document or something. That's just your answers to the homework. And that you have the week as well. So, and that'll go out Monday. So that'll go out by email. Both of those two will go out by email, and then you return both by email. Right. So, okay. So we get back on a compute node, and then we're going to use, I guess, the resource requirements that we've been just doing the whole business with, and get on a compute node. There we go. All right. So let's see. We didn't quite finish the module stuff thing. We talked about how like SAM tools is one of the things in the module system, but you have to load it. It's not just part of the default stuff when you come into Hoffman. There's this module command, which has all kinds of commands. I think is my window kind of below the bottom of the screen here. Let's make it a little smaller. And module avail shows you what's on there. And one of them is SAM tools. You know, like sometimes you have to like maybe case insensitive grep is better because you don't know if they capitalized it weird. And like I might even just try like case insensitive SAM just to see like who knows how they spelled it, but they just most of these are just all lowercase, it looks like, but you see like some like RStudio aren't, right? They're mixed case and whatever. So but there's SAM tools 1.11, 1.15 will use 1.15, and then you can do the module load stuff, right? So you do module load, and then now it's in our path, and we can run it and stuff. And not that you really have much need to, but you can always say module unload, and that puts you back wherever you were. And you can mix and match, right? You can have multiple things loaded at the same time, or whatever. Unload some of them, not others. Whatever you need to do. Okay, so yeah, okay, so then we were looking at just a BAM file to just kind of have something to play with. So that was this is the 2 lines that set up a shell variable that just points to a BAM file that I already have in my scratch space that just has a really long path name. So we just split the building up of the path name into 2 pieces there. But there is a file there, and it is a BAM file. I mean, the file command doesn't really understand bioinformatics stuff, but it kind of knows it's gzippy. But it ends in .bam. It's a BAM file. SAM tools is what we use to look at BAM files. The first command we did yesterday, the only command I think we did yesterday, was this view-h --no-pg, which is because of the defaults of SAM tools view. By default, it changes the SAM file. It shows you a little bit. These options make it so that it literally just shows you the BAM file with no changes. And what comes out, oh, you got to give it the file name. We gave it nothing. There we go. So there's the BAM file. Oh, I did a module unload, didn't I? So we got a module load again. Okay, there we are. So we're now looking at the SAM file, which is the uncompressed version of this BAM file. And we talked a little bit about how there's some header lines at the top here, and then there's some sort of meet lines, which is 1 meet line per alignment, which has data like the read name, the chromosome being aligned to, the position of the chromosome being aligned to, details about the alignment. Like here, you skip 41 base. You don't care. We're not going to, you don't need to know what the code is here, but this particular one means you skip the first 41 bases of the read, then you take the next 23 bases of the read in a gapless alignment. So this is actually a very fragmentary alignment. This read is not, most of the read is not aligning. I mean, the read's going to be the sum of those two, which is 64 bases long. So only 23 are matching. This is probably actually a false positive match. This is probably so short, you know, down in the 20s and stuff, you can just find a place in the human genome that just matches by chance. This is probably a false positive. And then like some of the other columns, like actually, I mean, some of it was like the mapping quality score here is 0, which means that the aligner is very unsure. This is actually where it goes. That's another hint that it's probably could be a false positive guy. This is the read sequence reverse complemented if it aligns to the minus strand of the genome. And this is the per base quality scores. And then these are like these key value pairs that contain data like the alignment score from the aligner and all kinds of stuff. I mean, this is a methylation alignment, which is why there's stuff, this tells you like stuff about like where the CGs, CHGs, and CHHs are and whether the read kind of, this is bisulfite converted reads. So you get data about the methylation status of each genomic cytosine, and this XBZ is an encoding of sort of the data out of the read in terms of that interpretation. Anyway, okay, so like then one thing we could do is this sort of kind of acts like gzip-c-d. And so if we want to pull lines out of this or filter this and so on, that just acts kind of like the thing that turns the BAM into text, and then we can play with it with any UNIX text utility that we know about. So suppose we wanted to pull out, like make a FASTQ file out of this, okay? Like extract the reads back out and make a FASTQ file out of this. Ignoring issues about like reads aligning to multiple places and this reverse complement issue or whatever. I mean, we're not really doing this for real. We're just kind of practicing. I'm just kind of giving you an idea of how you would work with stuff like this using the tools you now know. So that's the start of our pipeline. That gives us a plain text file to work with. Okay, if I want to make a FASTQ file, I don't want the header lines. So one thing I could do is I could do a grep, and at the beginning of the line, there's an @ sign, but I want the lines that don't match with the dash V there. So that strips away all the header lines like that. Of course, as it turns out, you can actually tell SAM tools, just don't give me the header lines anyway. And in that case, we can skip the grep. So I mean, here, if you read more about SAM tools view, you realize that if you just leave off all these options, its default is actually not to give you the header at all. So in that case, if we take away those options and take away the grep, and we now still don't have header lines, that's how we'd really do it. But even if it didn't have the option, you could just filter them out anyway. Okay, so what are the columns? No, okay, so another question is, what is the spaces, tabs, or whatever usual kind of stuff? So if we translate, you know, the usual thing I've been doing, spaces, underscores, tabs to @ signs, you see that essentially this is a tab separated file, right? So this is rename tab, something, tab, something. It's all tab separated. So let me go back to this way. And what do we need to make the FASTQ file? We're going to need read names, read sequence, and per base quality scores. The read names are column 1. The read sequence is 2, 3, 4, 5, 6, 7, 8, 9, 10. So remember 10, 1 and 10 right now. And then 11 is the per base quality scores, right? So 1, 10, 11. Those are the 3 pieces of information we need in the order read, sequence, quality score, which is luckily the same order they, just for ease of remembering, it's the same order they got to go in the FASTQ file, except the FASTQ file needs a line 3 between the sequence and the quality scores. But we can make progress here by cutting out just the 1, 10, and 11, okay? Or we could let awk do the cutting out as well. We have a choice here. So, but just even if we're just doing this just to kind of verify that columns 1, 10, and 11 are right, this is it. We're almost to FASTQ now, right? All we got to do if we look back to FASTQ is we need to put an @ sign on the front of every line And then we got to put new lines instead of tabs. We also have to put a single plus sign on its own line between column 2 and 3 here to finish the FASTQ format. So let me do it this way. I think the slides do it all in a single awk. All right, I'll do it the different way live. So let's do it with the cut here, and then the awk only gets 3 columns. So in this case, it would be okay to just use awk directly. Like this is going to be fine, but I'll talk about a point in a second. So we're going to print something. We're going to print column 1, column 2, column 3. But now we kind of got to get the formatting right. So we want an @ sign, and then the first string, and then a new line, and then so that's the read name with an @ sign on the front. And now a string, that's now the read sequence on its own line, and then a plus sign on its own line. That's the line 3 out of 4 in the FASTQ format. And then we need the per-base quality scores on its own line. That's the 4th line and the 3rd string in this print statement. And that should do it. And so there we go. That's a FASTQ file. In this case, like I said, it's kind of okay because the fields here have no spaces inside them. The only white space here is a tab here and a tab here. Sometimes you have columns that themselves contain spaces. And so the tabs are really the thing that separates it, right? So if you have like column 1 is a mix of things, some with spaces, some not, and then column 2 is over here, and there's a tab between column 1 and column 2. For some tools like cut, they'll only do tabs by default, and that would be okay. If you did cut -F1, you're going to get that first column, including the guys with spaces in them. They're going to survive intact, no problem. Cut -F2 would pull out the second column always, even if the first column has spaces in it. Other tools like awk, the default is just white space separated. So in awk, if you say column 1, 2, and 3, and don't say any options, those could be spaces, tabs, whatever. But if you have column 1 sometimes has spaces in it, then in the lines where it doesn't have a space, it's $1, $2, $3. But if you had like column 1 had something with a space in it, then like say it was something space, something tab, column 2, then $1 would be the first word of that column 1 guy. $2 would be the second word of that guy. $3 would be there. And it's no good because sometimes $2 is in column 2 and sometimes $2 is in column 1. So in that case, you kind of want to tell awk, it's a tab separated file. Don't pay attention to the spaces. The columns are defined by tabs. And like I say here, it's not a problem because there's no spaces. There'll never be a space in this or this or this. So it's not a big deal. But if you, just to give you future information, this -F option to awk is the field separator. And if I put a tab in here, remember that's this funny way we can have shell expand into a tab character. This now tells awk that you separate fields, columns by tab. That's what it is. And now even if columns 1 and 2 or 3 had mixtures of things with spaces or not, the $1, 2, and 3 would refer to the tab separated columns regardless. So because that's the intent here, that's what I would do anyway. You don't really want to just rely on the columns being right. If you know it's a tab separated thing, just tell awk it's a tab separated file. Right, so that's pretty good at this point. If we wanted to gzip it, we could do the gzip-c to do a standard in to standard out gzip compression, and then we could write this out. So this would be like this basically, right? So that is a BAM to FASTQ, a gzip FASTQ converter basically pipeline. Now that's going to take a little while because the BAM file's a little while. I didn't talk about this in the slides, and I think we'll have time. So maybe, let me just show you something that not really in the slides, and there's more to say than what I'm going to show you just right now. But this is kind of a new thing to let you know that the shell can do and UNIX can do. So this pipeline is running. It's going to take a while, and I want to kind of like do other things. So I could, of course, open a new window and start a new session of Hoffman like we did yesterday and have like 2 sessions running and whatever. But you can have multiple things running on one computer. In this case, the computer we're talking to is a work node. But if you have a Unix-based local machine, this works. Whatever. Well, I talked long enough that it actually finished. So let's have it go again. Okay, just so that it's still busy. I would like to do something else, but leave this running. You type Control Z. Okay, and now you see something you haven't seen before. What that says is job number 1, which is in the foreground, has been stopped. This is the pipeline, this is the command, and so on. And I got a shell prompt. It's stopped. It isn't actually running anymore, but it's not dead. It's just paused. So if I type jobs, this is jobs, not top and queue jobs. These are the current shell you're talking to's jobs. You'll see that we basically get the same line. That basically, when you pause it, you got the line in the jobs table that just got created. And jobs shows you the list of all the shell jobs that are currently in progress, but we only have one line. So I can do things with jobs. I can put them in the background where they'll continue to run. I can move them to the foreground where it's as if I had just kind of put them, hit enter, and they're kind of like we're waiting for it to finish and it's got access to our screen and keyboard. So I want this one to work in the background now. I want to be able to do other things, but have this keep running. So you type BG for background, and now you have to say what job you want to put in the background. Now, in this case, we could just put BG and it's going to know it's number 1 because there's only one choice right now. But the general syntax is %1. That's job number 1. So like in this list, this is job number 1, and that one it says I want to put job number 1 in the background. Okay, so now you see. Now it's running. And in fact, if I do something like, if I look at my jobs with PS, which is not a command you really know yet, but that shows you all the processes, the Unix processes that are running in the machine that you're on right. And you can see these are my SSH incoming connection here related to it. This is my login shell on this machine. This is the shell we're normally talking about. This prompt is coming from this path. But you also see all the parts of the pipeline, right? So there's a SAM tools, a cut, and an off, and a music-c. PS, of course, sees itself because it's running at the moment. It takes a snapshot of what's running. And actually, I did the PS, and the PS with these options would show you everybody on this machine. Then I just stripped out my username, or you could also spin off the PS and just show me my own, or whatever. So there's this graph is that graph, this PS is that PS, and these parts are coming from that pipeline. That's my shell, and this is my incoming SSH connection from the QRSH that we got here. So eventually the shell will tell you that your job's finished. So like you see here now, 1 done. And now it disappears from the jobs list. I have no jobs. So I could go dig out multiple BAM files and we could have multiple one of these running at the same time. Let's just use the same BAM file a couple times because I just want to show you having multiple jobs running at the same time. So I'm going to go up arrow again to make the 3rd time I'm doing this just to do it. So I'll show you something else. Suppose you know you want to put this job in the background immediately, right? I know this is going to take a while and I don't want to wait for it. You don't have to Control Z and BG it. You just put an ampersand sign at the end. And that tells the shell, I want it in the background right away. So now it's put in the background right away. And it's a running job in the background. But of course, you can now issue more commands. So you could have a bunch of these guys going at once. You wouldn't do it all with the same file, input file each time. You would have, really different things running. But now I have a whole bunch of stuff running at the same time. Right. So now you see I've got all of these things running at the same time. Now, like I say, Hoffman doesn't really enforce everything. So we asked for 5 cores. We're probably using more than 5 now because these are all running at the same time. So, that's like 1, 2, 3, 4, 3 times. So we're probably using 12, which means that we're we only asked for 5. We're kind of using 12. This is an interactive session, and most of our interactive session is going to be at a shell prompt where we're doing nothing. That's going to lower our average a little bit. So we're probably okay on average because like we're only bursting kind of like in this 12. We're not like saturating 12 for 3.5 hours that we asked for. But I know that's why like this cores reservation thing is a funny thing. It's like basically if this machine is idle, this machine is just going to run all the simultaneous programs it can at the same time. There's no reason to slow them down, and like only let you use 5. They could have done that in Hoffman. Like the Unix operating system does have enough features that they could say that, oh, you came in from a QRSH with cores 5. We're going to virtually subpartition the node you got landed on, and you processors will never be able to use more than 5 cores of that machine at the same time, even if the rest of the machine is completely idle. They chose not to do that in Hoffman, and sort of like every running process at a machine can fight for all the resources of the machine, even beyond the scheduling request. But this if we were really planning to kind of saturate this node the whole time that we did our QRSH, we should have asked for cores that are more in line with how much stuff we're simultaneously running. But that's anyway, so that's almost the full life cycle. You see here they all finished. Let me get a couple more running to show you some more commands. So you can get rid of them if you made a mistake or you don't want it to keep going. You can say kill. So kill job 3, and now you see job 3 terminated, but 1 and 2 are still running. And if you decide you have a command that you want to bring back, so like while they're in the background, they are sort of not connected to your screen and keyboard anymore. If you want to bring one back to the foreground because you need to interact with it or something, that's FG. So these are both running, they're both in the background now, but if I do like FG %1, that now brings job 1 back to the foreground. We are now connected back to him, and it is if we had just entered this command and hit enter, and if I type stuff, it's going to him, and if he prints stuff, it's going to come out here, and when he finishes, we get our submap back. So that's like that. Of course, you can then move things foreground and background multiple times and so on. It's no big deal. So get a couple more running. So I could bring job 2 back to the foreground. I could hit Control Z. Now it's stopped. Okay, so now you see it stopped again. I can put it back in the background. Now it's running again. I could move 3 back to the foreground. Now he's waiting. I could Control C number 3. That's basically a kill. And now 1 and 2 are still running. Anyway, you kind of get the idea. Yeah. Yeah, okay, so screen, I don't really recommend using screen much on Hoffman. You can kind of get away with it on a login node. You really shouldn't use screen on a work node. Because screen is designed to let you keep a shell connection running that you get from SSH, even if you disconnect internet to the machine. And that's sort of contrary to the QRSH job queue principles, right? Because you could end up having a shell running and processes running on the machine after your QRSH dies. So you don't want to, here's another thing you can actually do, but don't do this, right? So I'm on a login node. I can SSH directly to node 725, right? So now I'm on 725, but I'm on 725 and I am not tracked by the job system, right? And this is not part of the agreement you have with the Hoffman people about how you're going to use Hoffman, right? So the agreement with them is that you only use work nodes via the queue system. So I would only ever like SSH directly to node if like something horribly wrong had happened, and I have to like clean something up that went bad. I mean, it's hard to even explain what that would be. But if I somehow had like some job on a node that I think might have still left stuff running there, even though like the job died or something, I might SSH into the node, look around with the PS command or something, make sure that all my stuff is gone from there, then just immediately exit out. I think actually there's even an automated system process that if you hold a direct SSH connection onto a node for more than a minute, I think they kill you. It's an automated kill. They used to let that kind of happen, but Now you only get like a few seconds where you can kind of sit directly on a node. But if you need kind of a sledgehammer, kill all in your username like this. This will kill every process you have on the current machine. That's everything. All your running stuff, your shells, and your SSH connection. So when I do this, I'm going to pop off this node because everything I have on this node, including my shell and my QRSH, is going to die. So boom, right? I just exploded everything of mine on that node. But if you're like in some situation where things are like out of control or whatever, like you've got some script that's like in some kind of loop that's just kicking off stuff like continuously, and like you've got hundreds of things running, like it's out of control or something. You might try something like kill all and your username just because you need to like kill everything fast and so on. So I lost my QRSH that way. But so anyway, so this is actually pretty useful. For example, this allows you to do the kind of stuff we're going to do with the job queue system, but on your local machine, say. Like if you have a bash shell on your local machine because you're on a Mac or you're on Linux or you're on Windows and you've installed Cygwin, or you're in Windows services for Linux, on Windows subsystem for Linux on Windows, or you're on a virtual machine on Windows. So you're talking to a real bash shell. You can do this stuff on your own machine, and you can run multiple stuff at the same time on your own machine. Because none of this is all built into shell and Unix features. So when we do multiple jobs with the job queue system, that relies on the whole infrastructure of the UGE job software that's been installed in Hoffman. That you don't have on your local machine. But this stuff that I just showed you, this works on your local machine. So that's pretty cool. But that was kind of like a little side thing. We can actually talk even fancier, like we'll revisit this at the end of today, where because like I don't want to not get to what we're supposed to do today. But while we were here, I think I wanted to bring that up. So okay, yeah, we basically did this. Just to show you some of the other stuff, this is not a Python workshop, this is not an R workshop, but those are on Hoffman. So like, module eval, grep Python. Oh, is my window just so, it took a while to think about that one. Okay, anyway, so the most recent one they have in there is 396. So why don't I load Python 396. Now Python is a little complicated because there's Python, the core language, and then there's Python, the package manager systems. So that's why there's things like Anaconda and Bioconda and all these other things, because normally you don't want just base Python, you want Python packages. And those are, that's like another layer. And there's many choices for your package manager. And then you get into problems because a lot of packages are mutually incompatible. And certain software you want to run that's Python software needs certain combination of packages, which may be incompatible with a combination of packages another piece of Python software needs. So now you need ways to kind of have like multiple sets of installed Python packages that you can keep isolated from each other, which involves virtual environments and stuff. And the Bioconda and the Conda stuff is also kind of related to that, because in a way those are their own virtual environments. Anyway, it gets complicated, and that's something that the Python workshop should really talk about. But here I'll just show you base Python. Okay, so this is basically base Python 396 with no packages. Basically, we're not going to worry about the package situation. But at this point, I can do, Python 3. Oops, what's the demo command that I have you do here? No, yeah, it doesn't matter. You just paste in any Python code. This just adds two vectors, element wise. Oops. So this is a vector 1, 2, 3, a vector 4, 5, 6. The zip here just kind of does coordinating positions and adds. So the 1 + 4 is a 5, the 3 + 5 is a 7, and the 3 + 6 is a 9. Anyway, it's just at this point you can run any Python code. That's how you get out. R is in there. So like I think that's the most recent version of R that they have. Capital R is how you start R. And then you can do R code. The equivalent of that Python code in R would be this. Okay. and that's the quit, and we go. But anyway, so either we have an R workshop too. Of course, a lot of the time people use R or Python. They're also doing it on their local machine or whatever, especially R or whatever people like. There's fancier interfaces that involve graphics and stuff and whatever, and you're not going to get that with this base R base Python in text mode on Unix. But these are all topics for the other workshops. So just to show you that the module system has these things, and you might be using them. Okay, so now let's work toward shell scripts. Okay, so this one is pretty wide. So switch to your Scratch directory. That's the purple stuff here. So because to follow along, you're going to need to create files. So you need to be in your own Scratch space where you have write permissions. Okay. I'm going to get rid of all of these guys we just made. Okay, so you need to copy out the scripts and data you're going to need to follow along here. So this CP command is to get yourself your own copy of the stuff we need. Okay, so do that, and you should have a bunch of stuff that copies. You will not have permissions for this aside folder. That's fine. There's nothing in there that you need. That's just mostly for me in case things go wrong. I have pre-generated outputs for things, but I'll just do this. Okay, so and then CD into that directory. So now you're in your own copy of this thing, and you should have files that look. You're not going to have that directory. So it's not anything like that. You're going to probably have this. So you should have a couple bash scripts, which we haven't talked about yet, and some fastqgz files. And we're not. We use these as demos files yesterday. These are the files that are relevant for today. If you still have a copy of this, I don't think we copied this directory as a whole yesterday. Maybe we did. If you did, just delete that one and copy a fresh one, because otherwise you may not have all of these files, because I made some changes last night. Okay, so we have to decide what we're going to do in our shell script. So let's just make up another little task to do that exercises our knowledge of Unix utilities and stuff. So suppose this is our goal. Okay, so we've got some fastqgz files here, which are basically reads. These are now real reads, not index reads anymore. So these are longer than we had before. But we've got reads, ACGTN sequences. They're longer than they were before. And suppose that what we want to do is for each read, we want the CG content. Okay, meaning the percent of bases that are C or G, right? Because that's relevant to a bunch of things. And for each file is one sample. And for each file, we want to know the histogram of the CG content, right? So we're basically interested, like plotting like the CG distribution over the per read over for each sample, right? So how could we do that? So okay, so we already kind of know from yesterday we need to build this pipeline up in pieces and stuff. The next wrinkle that I want to include at this stage, though, is to immediately parameterize our pipeline so that the file name comes from a shell variable instead of just hard coding the file name. Because when we write this as a script and stuff, we want it to be able to run on any file we give it and not hard code the file. So let's start immediately by having our pipeline use the file by a shell variable. So we're going to pick one of these as the test input, like just the first one here. And we're going to call that FQGZ, okay? Yeah, okay. That's for FQ for fastq and GC to remind yourself that it's a gzip fastq, because how you would use it would depend on whether it was already unzipped or not. So FQGZ is just a little reminder that this is a gzip fastq file. That's the intent. And we have, we don't care what the file name is. We've got it set to one of our input files here so we can test out our pipeline as we go. But when we get to the final pipeline in our script, we want that to remain a variable because we want that to be able to be changed and for the pipeline to run on any of the input files. Okay, so don't worry about this line until we get to the very end, because that doesn't show up until this very last piece. So we'll talk about that when we get to that last part. So we're going to start right here. Okay, so first thing to do is, it's a gzip FASTQ file. We got to ungzip it. So that's our gzip c-d, leaves the on disk unload, spits out to standard output, the uncompressed copy. So that's where we're at. We have the plain text form of this thing ready to go. Now we want to histogram CG content of reads. Well, that means the read names, the plus sign separator, and the per base quality scores are all irrelevant. Let's get rid of them. So you remember our paste -- trick from yesterday? That's going to go from the 4-line block format to the 4-column format. Okay, like this. Now we can use cut to pull out column 2, and that gives us just the sequences. Now we're looking at the sequences. This is a good start. But now it's like, well, now what? Now we got to do like CG content. Well, what does that mean? We need to like count in each line. We need to like count the number of ACGTs basically, right? Because then it's like C plus G over A plus C plus G. If we want it as a percent, we got to decide what form we're going to express it in. Let's do it as percents. So we multiply by 100, and let's just round it to the nearest integer. Okay, so we just want like 0 to 100 as integers as the output. We don't want like decimals and stuff. So okay, so now we basically need to like count 8 letters in each line or something. So actually, awk is a pretty good tool to do that, but you probably didn't see in workshop 1A the sub or the gsub command in awk. That is the substitution command. It does search and replace. But one of the side effects of search and replaces is that it tells you how many replacements it made. So what you can do is, all right, so let's start here. So like, let's count the number of, to match the slides, what did I do? C's and G's first, okay. Actually, we've already diverged from the slides a little bit because the slides don't do the cut -F2. They just use $2 inside awk. That's fine too, whatever, it doesn't matter. We just arranged to give awk the single column that we need. So anyway, whatever. It's always more than one way to do it. It's not like there's a unique only one way. Okay, so let's count the number. I'll first show you just like how to count the A's, and then we'll make it to be the problem we really need. Suppose you wanted to count the number of A's, capital A's in a line. Then this is how you do it. So the first argument to gsub is a regular expression of what you want to match. So, and regular expressions in awk are delimited with like slashes. So like we're building up a gsub command here, but the first thing is the regular expression that's the pattern to search for. And here we would just say, search for an A, capital A. Or if we didn't want to care about upper and lower case, we could do this. That's a regular expression that matches up a single uppercase or lowercase a. The next position is what you want to replace it with. And here we kind of have a bunch of options. We could just delete them. We could replace them with the empty string, in which case they would just disappear now that we've counted them. We could replace them with themselves. That's fine too. It would be a bad idea to replace them with like C's or something, because then we're going to go count C's and we just like increase the number of C's. That would be stupid. So I mean, yeah, either you would delete them or basically keep them the same or something like this or whatever. Because we're not interested in changing them to something. We're just interested in counting them. And the output of the gsub function in awk is the number of substitutions. So that's why we're going to save that in a variable. The number of A's is this. And the third argument to the gsub function in awk is the string you want to search in, which for us is the whole line. First column would also work because there's only one column. So there's a bunch of options here, right? So I could put $0 here, $1 here. I could put a blank here. I could put the A here. If we know that the reads are all uppercase, I could just do this. I'm always nervous of whether there's lowercase in there or whatever. So it's just as easy to do that. Although the replacements would be all in uppercase, but like I said, that doesn't matter for what we're doing. But that's basically how you would count the number of letters of a given type. Well, usually there isn't a choice. So in awk, curly braces must be around the code that runs. The single quotes are there because the shell had, like curly braces are special to the shell, as is the square brackets and as is the $sign. So the single quotes are there to stop the shell from playing with the awk program. But most of the time you don't have a choice of which brackets is which, because the meaning of the brackets is what it is, and you don't get to really choose a different one. No, and there's not usually synonyms. So I mean, it's just like you have to use the one that means what you need it to mean. Okay, but we don't need A's, right? Now we could count A, C, G's, and T's separately, but for CG content, we don't need to distinguish C's and G's, they're the same. And we don't need to distinguish A's and T's, they're the same. So we might as well, instead of doing like 4 G subs, just do 2. So I'm going to count C's plus G's, or or C, G, whatever. I don't, what did I call it in the slides? I just call it NCG, right? It's just sometimes CG means the dinucleotide C followed by G. Here it means C's or G's as single letters, whatever. It's just trying to make the variable name mean something. So, but what should the pattern be in that case? It should be like this, right? Because now we're saying the thing you're looking for is the single letter, capital C, capital G, lower G, and that is the pattern. Just one letter, but those letters. What did I do for replacements in the slides? Did we do empties? Yeah, we just killed them. Okay, so we'll just replace them with empty strings. Just delete them from this thing. And okay, that'll count the number of CGs. Why don't we see if this is working? So this is not the print command we're going to need at the end, but let's just kind of see our progress. So why don't we print the count and what's left over? Okay, so I'll print out the column 1 again after we've done the substitution, and before that we'll print out the count of CGs, and we'll see if we're on the right track here. Let's pipe that to less, and we'll see what we got. And you'll see this is all looking pretty good. So I think actually, if you look back at the FOSTA file, I think in this file the sequences are all pretty much the same length, right? You see, I'm pointing at the speaker, right? They're all like here, right? So, and I'm holding the. Oh, that's the end already. How did I get to the end? They're not that long. Oh, I always probably they're only 1,000 reads. Oh yeah, okay, yeah. I'm like, why is he so short? These are designed to be small just to make it easy for us right now. And it's just 1,000 reads. So they look like they're all the same length. So but now you see that they're varying length. And that's because we deleted all the C's and D's out of them now. And this is supposed to be the count of what we deleted. And we'd have to really dig them out to see in detail whether they're right, but it's kind of looking good, right? Because this is only 8 and he's kind of long. And then this guy's like a 41 and he's a lot shorter. So, really, if we put 13 characters at the end of this one and 41 characters at the end of this one and so on the rest, they should all come back to be the same length again, right? I mean, that's whatever, but I think we're good. So, and you see the only thing that looks like it's left is basically A's and T's, right? So, okay, so we're almost there, right? Now we need, for the denominator, we're going to need to know the AT stuff. So we just do another one. I don't think we need the spaces around. And now we're going to do another G sub here. But this time we're going to count the A's and T's. Okay. We'll make this print a little bigger. We'll also print out the A's and T's. Oh, something went wrong there. What? Let's see. Oh, because I put look what I did. I put it in the wrong place. The pattern we're searching for is the null pattern, and the substitution is what the pattern was supposed to be. So essentially what it does is it matches at every place and does the replacement. Anyway, so that was an honest mistake. All right, so it was supposed to be that's the pattern and this is the replacement. Okay, there we go. All right. So now you see a lot of these are completely gone now, right? We deleted all the A's, G's, and T's, and there's nothing left. But if you didn't notice yet, some of those reads do have ends in them. And actually now we have to think a little bit, well, okay, that's good to know. But now the question is, what should that do to our arithmetic, right? Like, what do ends mean? Well, in this case, I think ends really are kind of like no data, right? Because you don't know whether an n is a CG or an AT. So you simply, I think the right thing to do in this case is you just treat them as missing data, right? You don't count them, right? So the numerator should be C's plus G's. The denominator should be A's plus C's plus G's plus T's. And ends don't show up in either the numerator or the denominator. We just don't know. We just delete the end basically from the consideration. So, okay, and then that leaves one last question, I guess, is that what if the read is all ends? Then the denominator will be 0. And then we'll try to divide by 0, and that's not good. So in that case, what's the right thing to do? Well, in that case, actually, the whole read is unknown. And basically the % CG content of that read is completely unknown. So we don't even get a number out of that read then, I think, right? So in that case, we just, so the number of numbers we print out isn't necessarily going to be the full 1,000 or whatever the file is, because some of the reads, if they're all ends, they shouldn't generate any data at all. So we just won't print out a number at all for those. Okay, so now we know mathematically what we want to do with the next step. Okay, so we've got our CG count, we got our AT count. Next decision is, if the denominator is 0, this guy's done. We don't do anything with him. We only proceed to print the CG content if we have a non-zero denominator. So you may not have done an if yet in awk, but in awk they look like this. Okay, so we haven't filled all the bits in here yet, but this is where you put the thing you want to test. So for us, this is easy. This is just, oh, what's the denominator? We could just make a variable. Why don't we make a variable that's the denominator? Okay, so the denominator is the AT plus the CG, right? That's the denominator. So now, if the denominator is greater than 0, then you see these curly braces. So the stuff between these curly braces will be run if the condition is true. And then you see the else, and then you see the curly braces here, and we haven't filled this in yet. But this is the code that will run if the test is false. In our case, when the test is false, we don't even want to print anything out. So in this case, I just can drop the else clause because I don't want anything to happen if the test is false. But now we're in the test is true stage, and now we need to do the arithmetic, right? So that is going to be the CG over the denominator times 100. All right. And the question is, what's going to come out from that? Because it's like, does awk do integer arithmetic? Does awk do floating point arithmetic? Because it is the first time we've probably done division, and right, and adding and subtracting and multiplying integers only gives you integers, but division doesn't necessarily get you integers anymore. So what's going to happen? Let's find out. So, well, one thing is that I didn't print a new line anymore. So I forgot my new lines. So all the numbers are mushed together. Okay, so I forgot the new line. There we go. There's the new line. And now I'm getting at least one number per line. And you see that looks like awk does some kind of floating point arithmetic. Now here we did the printing as a string. There's all kinds of formatting options here. I haven't even really explained these, but like D is for integers, S is for strings. The floating point numbers have all kinds of ways to control them. Like if you want to print, like here's one that says, give me one with 17 digits of floating point precision. That's essentially the full, most languages these days, because the hardware is like this, do what's called IEEE 754 double precision arithmetic. That's really like in binary, but it means that like if you print them out with 17 significant decimal digits, you always get enough information to completely reconstruct the original number. Anyway, so this is like the maximum that makes sense to print. So now we're seeing like all the digits that are sort of being carried there. You can put after that decimal point less if you don't want like all those. You saw the default was like a couple digits. When I did it as a string, it looks like aux default is like 4 digits after the decimal or something, or maybe 4 digits after the decimal or something. So we can like play around with different options here. Like I could put like .3f, and you're going to get 3 significant digits. So here you see, no, .3f would be 3 digits after the decimal point. So that's why you see 3 digits after the decimal point, so even if the number of digits in front varies. If I did without the dot, the 3 in front, that should be 3 significant. Well, maybe I should stop before I embarrass myself here. So anyway, we don't need to care because the one we need is basically like .0f, or what did I put in the slides? .0f, yeah, okay. That's basically give me 0 digits after the decimal point, and that is basically round to integer. So there's our integers. Okay. Anyway, you got to look up the printf in awk to kind of see what all the options are for how those formatting of numbers work. You get a lot of options there. I know why I'm confusing myself, because I'm using the f, which stands for fixed point. The usual one you use for a floating point is g, which is the variable, which counts the number of digits no matter where the decimal point is. The f is always counting after the decimal point. I think that's what I confused myself on. Anyway, so for here we want 0 digits after the decimal point. So it's %.0f. Okay, well now we have just a list of integers. We know how to histogram this stuff. We've done it like 1,000 times now, right? So now we just got to do a histogram. So we could sort numerically. We've never actually given like floating point numbers to sort. Like here, I'm on my local machine, not that it matters, but here's a scratch file with like some floating point numbers in it. I'll even use some with like scientific notation, right? You know, like the E notation, like 3E5 means like 3 times 10 to the 5th power, right? You know, so Excel does that too. Like a lot of software uses this like E notation for the numbers and stuff. And like here's a tiny one, right? Minus 6 or whatever. So sort-n, I don't think handles those right. No, sort-n is like for integers. It probably is sorting like numerically on like the integer prefix of these or something. So like this is a 0, this is a 1, this is a 12, and this is a 238, and that's what it's sorting in order. Doesn't make sense. The more general one in sort is actually called -g for general numeric sort. That understands the floating pointy stuff, which would also work for integers. So I guess strictly speaking, you don't really need the -n really. You could just use g for everything. But this one will actually sort the floating point numbers in order. So here you see the tiny one is first, then this one, then this one, then the big one here. So in this case, because they're integers, it's a question of style. But I think I threw G on the slides because I just wanted to try to give you guys more knowledge about what the options are. Okay, so that is going to put them in order. So now we've got like this. Then we know we got to do the unique-c, right? That basically is the histogram part once you've done the sort. That's our histogram. Now it's just a question of how would you like it? Do you want it with the spaces and stuff like this has got, or do you want the 2-column tab thing that we used to do yesterday? We could do that. So that was another awk, right? So then we do like the string, tab, string, new line, column 2, column 1. If you like the tallies in the second column rather than the first. And now we've got a 2-column tab separated histogram. Yesterday, I think every time we did a histogram, we sorted it by reverse frequency. This is probably a case where I would skip that sort, because in this case, the values being histogrammed are already ordered, right? They're percents, and they go from 0 to 100. And so like, this is the order that you would graph them in anyway, right? Like 7%, 9%, 10%, 11%, and so on. We could add a sort at the end here by column 2 reverse numeric. That's now by frequency. So 21% is the most common. But like, if you're thinking about like plotting a curve or something, you know, like this is now like, you could throw this in Excel or something and make like the little curve or whatever. Why would you, I mean, this is the order you want to plot on the x-axis anyway. So here, I think you leave off that last sort. It makes sense just to leave when the when the things being histogrammed are already themselves ordered, it makes sense to order the histogram by those, not necessarily frequency. So there we go. That's basically our, pipeline. And I don't even, how many commands does this have? 1, 2, 3, 4, 5, 6, 7. We're up to 7, right? 6 pipe symbols. If you don't count the less at the end, anyway, but hopefully you're starting to feel a little more comfortable about generating kinds of things like this and so on. This is maybe feels a little more natural than the first time you saw it. So now we're at the last step, which would be to write out a file, right? We've got what we want. We want to save this in a file. And so that's now this last piece that we haven't talked about yet. And since we're thinking about running this in a script and running it multiple times on multiple input files, it would be nice if the script would just figure out the output file name itself, right? Like we didn't have to specify the output file name. You just build the output file name as a modification of the input file name. So what do I mean? Okay, so this variable fqgz, this is our input file name, and it right now looks something like this, right? So, well, okay, we got to decide what we want to name the output file. So maybe I want to, so I'm just going to play around with it. Here I'm just using the command line just as a little scratch text editor. So I'm going to copy this here, whatever. So I'm thinking, okay, the .gz doesn't make any sense anymore. Let's get rid of that. But then maybe we need to add like a suffix. So then maybe we'll put on here something like this is a histogram of %cg and tallies. So, and it's a text file. So this is, you can name it whatever you like, but for histograms, this is usually the style I use. This is the thing that was histogram. This says this is a histogram, then double dash, and then I say what the columns are of the output. So the first column is the %cg, the second column is the tally. And this is just a plain text file. Or you could say this is a tab separated file if you like. I think like Excel knows like .tsv is a tab separated value file or whatever. So sometimes some people would call this a TSV, some people would call it a TSV, whatever you like. So the question is, okay, I can certainly type that file name myself for this one, but can we make the shell transform the file name itself? That would be nice. Because then when we use the script, we wouldn't have to say the file name. The script itself would build the file name. And the answer is yes. So how do we do that? So like I say, there is the guy. And now there are zillions of little operators you can actually do. The only thing we've seen shell variables we've done with them is just use them whole, right? We just pulled the values back out. But actually you can transform them as you pull them out. So one of the things you can do is you can strip off suffixes. So a % says delete suffix. And then you say what suffix you want to match. So this says, if there's a .gz on the end, get rid of it. So now you'll see the GZ's gone, the .gz's gone. Well, now I can do what I want to add on the end. And so that now builds the output file name from the input file name. And that's nice because now I can go back to my full pipeline, redirect the output, and what file do I want to write the output into is this thing. And let's see if we got what we want there. There it is. So this is kind of important when you're kind of wanting to make shell scripts and functions and stuff. You kind of want to like have them do as much work of the thing as they can. So like if you can have them figure out the file names, all the better, right? Because then one less thing to tell the script. So okay, so now we know what we want to put in our script. I mean, we kind of have our pipeline all figured out and stuff, and we kind of know how the file names are going to work and stuff. But now, like, okay, time to make our first shell script, basically. So, okay, so the first part of this slide is just summarizing everything from the previous slide. This is like the final answer from our previous slide. So this is us setting the shell variable to some sample file name, but this is like the pipeline we need to run, right? And then this does everything, and this is completely parameterized. As long as you have a shell variable set to the file name you want it to work on, this piece of code does the entire job and creates a output file name which is named in coordination with the input file name. So let's first do this as a shell function, and then we'll see it as a shell script. So to transform it to a shell function, pretty easy. All we got to do is wrap the function brackets. We got to pick a name for the function. So we could call it FQGZ histo %CG, right? Something like that. And it's going to take one argument, which is the file name, the fastqgz file name you want it to work on. And so we just say function, the name we chose for it, the curly braces, and then we got to put the body of the function here. Well, most of the body is just literally this pipeline we just figured out. Like this is just copied character for character here. All we got to do is connect the fact that the pipeline was written with the shell variable FQGZ being the name of the file name. And if we're going to get that from the first argument to this function, we just got to move it from position 1 of the arguments into that variable name. So we're just going to pull out positional parameter number 1 and put it into FQGZ, and then this pipeline can run just fine, and that will come from the first argument to this function. Okay, so we're going to place that in there. We now have that function ready to go. And now we can just say the name of our function and one of these files, right? So that's input file number 2. Bam, right? So, and now you see there's the second one there. Oh, it looks, I must have misspelled something at some point. Did I decide on hist or histo, or looks like the slides I chose histo. I think I usually, in my own work, usually just use hist because it's good enough, and 4 letters is shorter than 5, but whatever. Okay, so, all right, just to name this one consistently, we'll rename that one with an O. Okay, that seems to be the spelling we're using on the slides. Okay, so yeah, we can do the third one. You know, and this is pretty easy, right? In 5 seconds here, I'm going to be able to do all 6 of them, right? You know, so you know what? There's 2 left to go now. So this one, tab completion can do the work too. There we go. So there we are, and that didn't take that, you know, no time at all. But here's the next sophistication: shell loops. So we haven't really talked about shell loops yet, but clearly we just did some repetitive work there, right? We just kind of were given the same command over and over again with just a different file name. The file names, we know the shell can sort of do that for ourselves. If we just did like srx star fastq.gz or something, that would give us the file name. But how do we kind of run our function multiple times with different file names and stuff? And the answer is shell loops. Okay, so like first we're going to just do a stupid loop, right? So like this. Okay. So the syntax is, there's actually 2 syntaxes for loops. This is the one of them. So you say for, and then the name of the variable, the shell variable that you want to use. So I just used X here. And then you say in, and then you give words, however many words you like. These could come from file name expansion, brace expansion, whatever. Just, you got to give a list of things. You know, just here they're white space separated, but really what matters is their shell word separated. Whatever the shell thinks would break up into individual arguments, that's what the units are. And then you say semicolon, because you got to somehow indicate that the list is done. The semicolon does that. And then you say do. And now you're inside the for loop. Inside the for loop, you put whatever commands you want to run, but now you can refer to shell variable X, which will be different each time through the loop. The first time through the loop, X will be this. The second time through the loop, X will be this. The third time through the loop, X will be this. And then you have to somehow say where the body of the inside ends. And the way you do that is with the word done. And you saw also the shell prompt change, because shell knows that you're in the middle of something here. You haven't given me a complete command yet. So all I did here was echo the X back out. So we just see the 2 of them here. You know, I could have changed that to a touch or something, and now you'll see that. Now you see that we made those files instead or whatever. The body could have had multiple commands. You know, it doesn't matter, right? So, so how would we how would we call our function repeatedly? Well, for I suppose we should call it FQGZ for consistency, but it doesn't matter, right? So for X in srx star.fastq.gz do, and let's do some little logging kind of information as well. So we'll log what file we're doing and what the date is. I'll talk about this date thing in parentheses in a second. You could leave that echo line off. That would be no problem. I was hoping the shell tab completion would complete the file name of the script, but I'm not sure it does that. So we'll grab the file name of the function there. And in the loop I'm doing here live, I just called it X. On the slides, it's FQGZ, but here the for loop variable is just X. So I'm going to call my function with X, and that's it. So I mean, obviously these are very fast, but this could have been a very long list, and they could have taken a lot of time to do each. Even cooler if they took a lot of time each. I could have put them all in the background. I put an ampersand there, and now our loop is just kicking them off, and they're all going to run simultaneously. They're too fast, so I didn't catch them while they're there, but for a millisecond we had all 6 of them running simultaneously. That makes more sense when the jobs are longer, but anyway, I mean, you could already automate quite a bit of work this way. So to go now from function to script is a pretty small step now, right? So remember what our function looks like. It's this, right? So now we're going to make the script version of that, okay? So that is already here in a file called histo%cg for single FQGZ. So it's this guy, okay? So if you just cat it out, there he is. And it's on the slide too, with a few colors. So I'll refer to it on the slide. But this right here is the same thing as what's here. So first of all, there's this first line, which we've never seen anything like this before. This requires explanation. But the rest of it is pretty much the same. I mean, we're only doing the body of the function because essentially the name is going to be what the file name of the script file is. And we just don't need the curly braces on the outside then. We're just kind of, of course, the file is the inside. So you don't really need the curly braces to delineate the boundaries there. So basically this is literally the inside of that function right here. And that's literally what you see here. So essentially, the only changes were you got to add this line on the front, and you got to put it in the file. So let's talk about this first line. This is called a shebang line. This 2-character combination, which is £! Exclamation point, but a lot of people have like 1,000 names for this hash mark character. Some people call it £, because in the US, that is our shortcut for POUND. Like if you want 3 pounds of apples, you can say like 3 hash mark. That's like the abbreviation for pound. And I think that's the oldest way we use it. But some people call this hash. Weird people call it octothorpe because it has 8 barbs. It's like 2 lines like this. Count the number of sticky out parts. 1, 2, 3, 4, 5, 6, 7, 8 octo. It's like octothorpe means like 8 points or something. So it's, I don't know. Most programmers probably call it hash. It's easier to say. £! is too long. Octothorpe, no. Hash, very easy to say. That's what most programmers would call it. And exclamation points, similarly, exclamation point takes a lot of effort to say, but bang. Bang's a lot easier to say. So a lot of programmers call exclamation point bang. It's just due to the way we use it in English. So that 2-character combination is called shebang. Why did hash turn? I don't know. That's just what it's always been called. It is a magic sequence that the operating system understands. So when the Unix, because now we're talking about making a program. We haven't talked about like making code yet for Unix. So like if we look at like where's the cat command, it's in user bin cat. And if we kind of try to like look inside that file, it's code. All right, okay. That's a native binary that the operating system and the processor inside the computer understand directly. Our shell script is not of that type. Our shell script needs an intermediate program to interpret it before it hits the processor. That program is the shell. So in Unix, if the executable file starts with shebang, it is treated as what's called a script file or an interpreted file. If it doesn't, then it's tried to be done as a raw binary executable file like this one. And what comes after the shebang is the interpreter program. What program is the intermediary that understands the contents of this file and can translate it into actual code that can really run? And in our case, it's bash itself. And so where is bash on the system? It's in user bin bash, I guess, but it's in bin bash too. I don't, it must just be due to the, it must be in both places on Hoffman, and then the order that it is in our path matters. So, okay, so it finds the user bin bash first, but they're almost certainly exactly the same. I'm sure they're exactly the same. Yeah, and I'm sure if you MD5 some of them, they're going to be the same. It's the same file twice. I don't know why they put it in both places. The traditional place would be bin bash. So this is telling the operating system that should you try to run the script as a program, you must really give it to bash, because this is not raw binary code. This is a script that needs to be interpreted by the bin bash program. So that is the purpose of the shebang line, and you just start your scripts with that. But that's really it. So here is our script file again. Remember, we just give it a name that's something. The .bash is not required. That's just a convention I follow because I like to, it's just like a file extension, right? It just tells you this is a bash script, right? Some people would just call it .sh because it's a shell script, but you know, it's like a more subtle question. Did I use any features that were specific to bash? I just use bash all the time, only bash. Just write all my scripts assuming bash, and I don't even really think about like portability issues so much. So I just kind of write .bash in my script files because I know it works in bash. I'm not really sure it works in other shells. So, you know, a kind of .sh kind of suggests that it's sort of like a portably written shell script. Other people would just not put an extension on at all. I think the Googlers like to do that. They would just call this, they wouldn't even put the .bash. They would just call this file just the naked thing with no extension. Whatever, that's just, it's just all style. The operating system doesn't care, bash doesn't care. That's just all, you know, just conventions for yourself. So yeah, literally all we did was kind of create a file with a name that's going to be the command name of this thing, put a shebang line bin bash on the front, and then the body of what used to be our function, and that's it. Okay, so can we use this in the same way as we use the function, basically, is now the question. So let's try. So here is the command name. So I will put that first. And then let's to make sure that we see this working, I'm going to delete all the guys we just made, right? So that's, I think that's all the S star, T, SVs, and TXTs. Oh, got to match the brackets here. Okay, so those are the files that I think we just made. I don't want them still here because to prove to you that we're like doing it the new way, we don't want to have the old ones to confuse us. So I'm going to delete those. And now we're back to the way this thing was when we just copied it. Okay, and then we'll take a break. Okay, so here's the command name. Here is the file name for input, right? If it's anything like our function, this is supposed to be the way it's supposed to work, right? Let's find out what happens. Command not found. Why is that? Well, we know about the path, right? And the question is, the way bash finds programs that you don't tell it explicitly what the path is that they have to be on your path. And if you look in here, the current directory, which is this, is not on the path. And that's why the shell can't find this script file. So we have options. We could add the directory that the script is in to the path. That's like the most painful option. And there's not really much point unless you're going to like really use that script all the time in your work everywhere. And then you would probably make the path changes in your startup scripts if we haven't talked about startup scripts or whatever, but we don't have to do that. All we got to do is give Bash a little hint. We got to tell Bash the actual path to the script, because your search path in the path variable is not going to find it. So I'm going to up arrow back to the thing that didn't work. Now I have to give a path to the script. One option is to give an absolute path. So I could give the absolute path to this thing. That would work. Well, permission denied. We've got another problem, but it's not command not found. Another option is to give a relative path. What is a relative path to this thing? // in the current directory, this file. And because that's got a slash in it, that now tells Bash, don't even try to use the path. I'm giving you the path. This is where it is. So that's also going to give us a permission denied, because we have another problem, but neither of those things give us a command not found problem. So that was problem number one, is that it wasn't on the path. Problem number two is this permission denied problem. And that's related to the discussion we had on the first day, where executable things need the X bit. And if you look, I carefully on this first one, I took away the X bits so we would have this problem, so we would have this discussion. On the other two scripts that are already here, I've got the X bits on them. But you see, the X bit isn't there, and that's the permission denied problem. So we have to do a chmod of some type to get the X bit on there. So I'm going to do A plus X, because this is RWRR. I should add all three X's there, because why would X be, if it's readable by everybody, why not be executable by everybody? Why would it be why would those two subsets be different? So I'm going to add the X bit to it. So now you see that it has an X bit. In fact, actually, LS is also helping you out here. We haven't explained how the LS is managing to magically colorize everything. You know, like how it does. Like, why does this come out in red and this in green and stuff, and most text in black? We could talk about that at the end if you kind of want to know. But actually, you see what the trigger for green is. It's whether it's got the X bit or not, right? So you see, like, the black ones are ordinary files, but the green ones are executable files. So the fact that these two are in green, this isn't, but now they're all three in green, that's the difference. I think the .gzs are in red. It's got a whole ton of rules, which are completely configurable, but I don't exactly know what the HODMA defaults are. But I think there's this environment variable, which is a shell variable called ls colors or something. This is the magic rules. Yeah, this is yet another like mini language that you have to read like the man page of ls for. But this is basically encoding all the rules for how we'd like the files to be colored in our listings and stuff. Somewhere in here, there should be like, well, I don't even want to get into it, but somewhere in there is like .gzs are going to get a color and whatever. Let's not get into it. But anyway, so we solved our two problems. We know how to tell Bash to get away the command not found. We got rid of the permission things. We think now maybe it works. Okay, so up arrow. Let's do this one. This is the relative path. / script name, file name. It works. And that's all there is to it. It's pretty simple. It works. We could then do, I think I must do this in a loop then, the next thing here. So yeah, the next thing to do is to just do a little loop. Okay, so we just do the same loop we did before, basically, for x in srx star dot fastq.gz. Do / the name of that thing. Now a shell actually tab completes it, because actually the shell knows that if you're looking for a script name and it's not executable, it's not a script, so I'm not going to complete against that. So now that it's actually marked executable, tab completion wakes up and kind of says, oh yeah, I'll tab complete that. You're typing the first word of a command, so you're looking for commands or scripts, and that is the script, so yeah, that counts for tab completion. So that's good. And then we got to give it X now, and then done. I didn't do the echoes this time, so for the progress, but there we go. And now it's done 6 times with our little script. Of course, we could have actually put this for loop in another script. Like, some people believe that, like, as you do your bioinformatics analyses, like, you should never you can experiment directly in the command line, but once you kind of fix your analysis, you should always put that in its own like script file and only run like your final analysis from your own, like from a whole script file, because that lets you reproduce your work, right? Like, so that's like, because like if you're just doing commands like this and you don't have like a complete record of like everything that went by in your terminal, you may not, you're not really recording like, like web people have like a lab notebook and stuff. Like what's the equivalent for bioinformatics people or whatever? For some people, the bioinformatics equivalent of a web bench lab notebook are things like all the shell scripts that completely contain all the commands that they ran to do some analysis task. But there's lots of ways to organize your bioinformatics work. But some people, it's a matter of discipline too, right? You got to really discipline yourself then that says that like every time you get something done, you've got to like really, like write it in the script. And then to really know that that script works, you should sort of like delete all your outputs and run the script again. It's like, it doubles your work really, because you got to run it again to see if like it really works and you're not just like making some kind of errors or something that's not quite the same as what you really did over here in the script. But it's a discipline thing and so on. But some people do believe it's important enough to do it that way. What else? Oh, okay. So actually, it would be kind of nice if like the script could directly handle multiple file names itself. Like the way we wrote this script, it's fine, and we can just wrap a for loop around it anytime we need it. But in general, commands take multiple arguments, and why not just have the script take multiple arguments and then it just works on all the files there, whatever. So that's actually a really easy transformation. So that's this next slide here. So yeah, I said we were going to take a break. Should we do this? But we'll take the break now. So let's take a, I guess we're only doing one break. Let's do a 15-minute break, 3:15, because that way I'll give you time to do the feedback thing. And you're picking up the did everybody sign in the sheet? Yeah, she hasn't come yet. So yeah, okay. No, this is like halfway of the day. So she was here for like 2 hours of the middle day. Yeah, yeah. Okay. So I'll go to the restroom myself. I'll give you time. Did everybody get a chance to finish? Okay. Okay, so when we were left off at the break, we had this as our first script, which was a pretty easy transformation from our function version of this. And we just had to learn that you have to give a path to this thing since it's not on the shell's path. And we had to give it the X bits to make it executable. And then we were able to just, then we were able to run it like this. And, it looks just like our function invocation, except this is the name of it instead of the function. And then we put it in a loop, right? So then we did an external loop. The shell script only does one at a time. So here was our loop where we did all 6 of them. But because scripts are, they're like commands, and commands can get multiple arguments, it kind of makes sense. Well, why not just make the script able to handle multiple arguments and do multiple files? So let's do that transformation because it's an easy transformation. So here is the version that we have right now that only does 1. And here is, in this other file, is the version that does however many files you get. And what's the difference? Shebang line is the same. The meat of the pipeline is exactly the same. That's this and this. The only difference is that this one has this line and this one has this for loop. So what's the difference? Well, the pipeline is designed to work on file FQGZ. So in the one just handles one file version, we just set FQGZ from the first positional parameter, and then we go into the pipeline, and then we're done. So in the multi-file version of it, all we have to do is some kind of for loop that does the meat pipeline once with FQGZ equal to the first argument, the second argument, third argument, fourth argument, and so on. So this part is not really surprised. We just do for FQGZ in something, do done. And we're going to repeat the pipeline once for every argument. The only thing you don't know right now is how do I say all the arguments, right? Because it's like, I don't know how many there are, right? Like, I can't just put like $1, $1, $2, $3 or something, right? That would be exactly 3, but like it needs to be however many there are. So this is shell magic. This $@ is magic that just turns into a list that's exactly the same list as this thing got as command line arguments. So if we pass in 3 arguments, this will turn, it'll be for FQGZ in ABC, those 3 arguments and so on. And that's all that it is. So that it's a very small change. All we had to do is change this line into this little for loop. And the thing that the for loop operates upon is $@ just all arguments. And so with that change, and that guy's already marked executable. So let me delete the tallies again because we're about to make them again. We want to make sure that they're new and not like just carrying over from old. So, I was going to mention, oftentimes with dangerous commands like RM, you should do what people call pre-flighting. because we're, especially once you have like path name, like these stars and stuff in your path name expansions, you kind of want to know what those are before you actually do the commit. So it just means that instead of doing RM, you just do an echo, right? So like you could do like echo RM srx star tally.txt. I think that's the right pattern. But because I put the echo in front, I'm going to see the command and not run the command. And now I can inspect that and say, is that what I intended? If you're really just focused on the file name part, that's a little ugly because it's kind of like all this mush, like it's hard to read. You can do just ls-1 and then the pattern, because ls-1 means put it all in a single column. So basically this just expands this to a list of file names. ls just kind of goes and just the -1 just means put them in a single column. So if it's, it's easier to just kind of like see this and like kind of, oh, that's the files I want in this kind of mushy thing. But depending on what you're doing, if you're just worried about the file name part, then you can do this. But if the whole command has like complicated expansions in it and stuff, and you really want to kind of see the whole business, just throw an echo on the front of the command and you'll see the entire expansion before you run it. And then when you're ready to run, you just take away the echo and then you do it. But that people call that pre-flighting. You're just kind of seeing what's going to happen before you do it. Not worth doing for every command, but for dangerous commands, it might be worth doing. Okay, so yeah, we have the many version of this thing now. And so it's going to have to be /. We have to get some path to this thing, right? Because it's not on our path variable. But now we can take advantage of the fact that shell path name expansion can create the file names for us. So now I can just do srx star fqgz, because the shell will expand that into a list of file names. And the for loop inside the shell script will then go through one at a time. And there we go. And that's pretty nice. It's hard to ask for more than that, right? I mean, that's about as nice of an invitation to do this task as you could ask for. And hopefully you feel that the steps to lead to this point, they're I think they're manageable to get, to this point. So so that's a very common pattern in shell scripts, just to do something over every argument. So that for x in $@, blah, 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 done, that's a very common pattern. You see that all the time. Yeah, so we just did this slide. Okay, so it's time now to do the last part, which is to actually do these as jobs on the Hoffman queue. Not such a big deal here because they're so fast and they don't have so many of them. But suppose these are alignment jobs or something and they take an hour or 2 hours each and you've got 100 of them to do. This is not the way you're going to want to sit and babysit your interactive session to do them. And you saw that we can use the ampersand thing and get multiple things running. But the only disadvantage of the ampersand thing is that it all happens on the node that I'm logged into right now, whereas the cluster is 800 nodes. So essentially what we need to do is to be able to kind of like let the scheduler just choose the machine that the script is going to run on. And that's what the queue sub is going to do for us. And then we can submit hundreds of entries into the queue, and the scheduler will figure out all the details about what machine when, which ones have run, which ones haven't, and all that business. And we just kick them all off at the beginning and then monitor progress. And then just when they're all done, then we can proceed to the next step of our analysis. So how do we do the Hoffman? How do we put jobs into the Hoffman? This is what we got to talk about. So essentially shell scripts are what we run on the job queue. When the job queue kicks off a job, it will start one of our shell scripts. So that's how we control what happens. So we know how to make shell scripts now. So now it's a question of, well, how do we get scripts into the queue so that they're going to run? Okay, so that's the part we talked about now. So we're still in your personal Scratch space, okay, because you've already got all the files you need to do this in the copy that you've already done. So sitting in your personal copy of your Scratch space with these files here, we're going to be able to do the job queue stuff. So the command is going to look something like this. Okay, so this is going to submit one job, and what that means is that it's going to kick off the script once on some node of the scheduler's choosing. So queue sub is the command that adds an entry to the queue. Queue submission is what it stands for. Then it takes a whole bunch of arguments. Some of the arguments are about just kind of like basic stuff about the job, how you want to treat the job as a job. A lot of the parameters, these yellow ones, are the same resource requirement parameters that we've been using in the QRSH. Exactly the same as the QRSH. Cores, memory, how much time limit. So that's exactly the same with exactly the same syntax as you had in the QRSH. I mean, the numbers that you choose may be, different or whatever, but that's the syntax for those you've already seen. It's the same as goes in the QRSH. Then at the end, you put the script you want to run. And because you're not actually running it at this moment and QRSH knows to look in the current working directory to start with, you can put / here, it's okay, but you also don't have to put / here. So you just name the script that you want to run. This is one of your shell scripts. And then after that, you can put command line arguments to the shell script if you'd like. So if you put nothing after this, the shell script gets started with no arguments. But the stuff in purple here, just that comes after the red, those go as command line arguments to the script when the script gets kicked off on the node that it chooses. So yeah, so it's basically Q sub, then there's some jobby stuff, and then there's the resource requirement stuff, shell script, arguments to shell script. Okay, that's the syntax for the Q sub command. So let's now talk about the parameters we haven't talked about yet, which are these black ones here. Okay, and then this is the description of them here. So the first one is the most important probably, and that's -CWD. So Q sub doesn't follow the normal conventions. That's not like -C, -W, -D. That's actually a long option, but Q sub doesn't spell them with double dashes in front. It just uses single dashes in front. Whatever. But anyway, this -CWD is the most important one because it controls the current working directory that your script will have when it's kicked off on the other node. Because when it gets kicked off on the other node, that's going to be a fresh shell doing that again. So it's not going to necessarily have the same directory you are in right now. It's like logging in again fresh. It will have no variables, no functions. It'll be in your home directory, whatever. It's a fresh situation. So what the -CWD means is that the Q system will arrange that when your script gets kicked off, the Q system will make sure that the current working directory that script gets when it starts is the same one that Q sub has when you submit the job, which is going to be the same one as the shell that you're using to give the Q sub command, which if we give it right now, it's going to be in your scratch directory right here. So it's kind of what you want. It's like wherever you give the Q sub, that's going to be where your script starts life, which kind of makes sense because I would generally recommend in all your work to try to not have absolute paths as much as you can, because that means that you can always move things around and things still work. Try to always kind of arrange your work so that everything's in relative paths, because then you can reorganize your files at any moment and everything still works. Whereas if you always have absolute paths, you're completely locked to that arrangement, because as soon as you move anything, then you've got to find all the places that refer to that path and change them. So yeah, try to do all the work with relative paths. So the -CWD assists with that because it means just kick off the Q sub in the same directory that you want the script to have as its working directory. So that's how that works. The no is the Q system has abilities to, like, if the script died and stuff, or like so on, like automatically restart the job. You don't want any of this kind of stuff. You just, like, if it died for a good reason, like your script is broken or something, and you don't want it to like retry infinitely or something. That may be the default. I don't know. It's so scary to contemplate like the Q system going crazy. I just always put no here. It's just it just says don't try to no auto restarts. The no is related to the logging, which we'll talk about once we run one, and you'll see what logging comes out. But it basically keeps standard out and standard error separate rather than combining them in one file. And the MAS is related to email. So if you haven't done it already, and you haven't probably done it because why you don't have any reason to, but in your home directory, you can make a file called .forward. Okay, so tilde, remember, is a shorthand for your home directory. So for me, it's the same thing as you home cfocus.forward, whatever, same file. Make a file called .forward, period, FORWARD, all lowercase. It's a single line of text. Its contents is your email address. That is how I don't know what the Hoffman people do when you set up your account or whatever. The simplest thing is to just kind of say where you want your email to go, and that's how you do it. So the only entry I have in that file for me, it's a one-line file that just contains my email address. So if you haven't made that file yet, and I'm sure you don't, because it's like, why would you? Because you have no reason. But you're about to have a reason. So do that, because that's the email address that the queue system will use to notify you of serious situation. So I'll give you a few seconds to do it. Okay, so the AS, you can actually put all kinds of letters here. You have to read like the Q sub documentation to figure out all the letters that go here. But basically, every possible action that happens in the queue system, you get to choose, do you want an email or not? I recommend not like having most of them send you email, because otherwise you'll get zillion, like thousands of email messages. If you run a lot of jobs, you don't want to know like when every job starts and every job stops. More like I would say get email when the serious things happen. So what's the serious thing? Things like a job is aborted, like it dies unexpectedly, or like one of the administrators kills it or something for some reason or whatever. So like this AS is sort of like only like the most severe situation. So a job that just starts and ends normally is not going to send you any email at all, and that's generally probably what you want. If you want at some point, you can read the man page for QSub or whatever, which is it's very hard to read, but you'll find there in somewhere the -M option, and then there's these little letters that have what events cause email to you. Then there's this -N. The last one to talk about is this $N, and that's simply a job name. And I mean, that can be kind of anything you like. I would keep it short. Other people can see it. Don't, it's something that anybody in the cluster can see. It's just a reminder for you. It does show up in some file names for the logging and stuff. It's just, if you're doing alignments or something, you might just call it align one, align two or something, whatever. I mean, you just pick some short name that makes sense to you. Here we're going to do the same script we just made, which is this histogram CG content script. So I'll call it histo1, or we could call it histo CG1 or something, right? That'd be fine. And that's it. So okay, so like actually this one here is runnable. Okay, so it has this name in blue, which is fine. The resource requirements I've actually chosen fairly small ones here. Just one core, 30 minutes, 4 gig of RAM. 4 times 1 is 4, so that one's 4 too. I didn't bother to use the shell arithmetic there. This is the shell script we just made. It doesn't matter whether we use the single or multiple version, because we're just going to pass one file name here. And here's the first file to do. Okay, just as our first job. So I'm going to copy that out. You can copy that out and give that and enter it, and you will see that it submits it to the job queue. Now I'm going to quickly do some my jobs to see it, because if it starts fast, then we're not going to have much chance to see it. So I'm going to do this, and then we're going to talk about it. Okay, so it actually already ran and finished. So okay, so what you saw when the Q sub happened was you get a message like this. Every job has an ID number. This is a global unique ID number. I'm not sure. I think they reset it once, like 3 or 4 years ago or something. Maybe when they do like a major OS upgrade in Hoffman, which isn't too often, they reset the queue like back to 0 or whatever. But essentially, this is like a globally unique serial number, and it just keeps going up by 1, right? It's not a serial number tagged to you. It's just every time anywhere on the cluster at any moment somebody does Q sub, they get the next number in the serial number. So this is job 2,786,966. If you guys just ran yours, you guys should have numbers that are close to this, but should be a little different, because we all need unique numbers. And then this is the name of the job, and it says has been submitted. And then the next command to learn is my jobs. That shows you all the queue entries for you right now that you have either in flight or pending. Okay. So in fact, you see that I had 2 jobs either in flight or pending. Why is that? Because your QRSH counts as one. Essentially, QRSH is Q sub into an SSH. So it's done as just a job like Q sub does, really. So you see this QR login, that's just the job name it had. So this is my QRSH session to node 760 that I'm on right now. You see its ID number is actually a little bit in the past, because in the time since we started this at 130, the job numbers were in the 2.78 million, but in the 4,300 range, and now we're here at 330, and they're already near 7,000. So that's how many jobs the campus has been submitting in the time that we've been talking today. You see that the QRSH one is in state R. The R means running. So of course, the QRSH that's what I'm using right now. So that one's running. But you see that the one we just added, which is the 2786966, that's the agrees with this number here, and that's the name of it, HistoCG1. You see that its state is QW. That means queued waiting. So it is in the queue, but it is waiting. It has not yet been assigned to a machine. It is waiting to start. This is the date and time that it was submitted. Well, if it was running, this is the date and time it was started at. If this is waiting, this is the date and time that it started waiting. This is the time it went in. The rest of this information here is related to where it is running. Because this guy's waiting, he hasn't been assigned yet, and this is blank. But you see that for my QRSH session, I've been assigned to node 7060. And this part is more mysterious. It's MSA SMP.q, but essentially there's many queues. And there's different rules for who can use what queue and have how many spots in each queue and whatever. And we generally don't care. And so this is just the queue that we got put into by default here. So it says this job is part of this queue now, and it is running on this node. The slots is how many cores you asked for. So this job is running with five cores on node 7060. The job that we put in queue waiting has only requested 1 core. And this is related to job arrays, which is a topic for workshop 36. This is the more advanced way of using the queue system that we won't have time to talk about. But that's it. So you can just keep kind of hitting my jobs. And eventually, so this one is so fast that we don't really see the running stage. It's sort of, as soon as it ran, it was like a second. And so we'll run a second example today that takes a little longer, so you'll get a chance to see them in the running state. But basically, this guy was finished so fast that as soon as he hit R, he was done. And so we never got to see him in the running state in the queue. But you see here that after he finished, he's just gone, right? So the queue itself doesn't list jobs that have completed. It's just the jobs that are either running or pending. Once they're done, they're no longer shown. So let's now look and see if we got any new files. So if you look in your directory now, you should see that, oh, did I forget to delete the old guys? Anyway, we should probably be able to tell from the timestamp. So if I sort by time, LAT, the T is for time, sort by time. Let's sort all the text files by time. This should at least convince you that this one is a newer file, right? So this is the last time that we did, I think this is the ones we did from the for many GZ, the many version of the script. And that was so fast, they're all going to be the same 3:20 p.m. But this 1532, this is the one the single job we submitted, he just ran. So I forgot to delete them to show you that it was going to regenerate, but the timestamp got updated. So maybe that's enough to convince you that it ran successfully, or you've got the copy on your own that hopefully just ran and finished. Hopefully you're still not waiting. Your job should be pretty, these resource requirements are so low, the queue system should be able to satisfy them easy. One of the things the queue system can do is that as the job requirements get really small, the job system for the bigger jobs has to actually actively work to clear out space for those. But suppose it's working on trying to clear out one node completely for a big RAM job. Well, so he's busy trying to get jobs that are on there to finish, but then once they finish, he doesn't start any things there because he's trying to open up a hole, right? But if there's a job still running on there that he needs to wait for it to clear off before he can start the big guy, that job still has another 3 hours in his time slot or something, and your job is a 1-core tiny RAM half hour, that's a hole he can fill with your guy, for sure. So essentially the schedule is always full of holes because some people's jobs just require a lot of resources. And so it's sort of if your job requirements are small, the scheduler loves those because it can just stuff you in all the holes in the schedule, and those kick off really fast. So that's an argument for kind of keeping your resource requirements as low as possible, because generally you don't have to wait long at all. And we could probably get like 100 jobs like that, like kicked off at the same. If they ran for a few minutes each or something, we could probably get 100 in flight at the same time. So I'm sure there's that many holes across the cluster right now of that size. Okay, so you see, the script ran and it did its work and everything's fine. You also see we got some log files. So that's these guys here. You see that they're actually named by your job name, right? Remember that -n argument. So that's the name that they get. And then there's a dot, and then there's this EOPEPO. The E stands for standard error, and the O stands for standard output. The P is related to this PE shared business. Remember in our resource requirements, we have this PE shared one. That's the one means one core. That's called the PE stands for parallel environment. And there's more ways of using, like some jobs are fancy and they want to use a lot of cores, but not just on one machine. They actually want to use cores on multiple machines. Like for example, big RAM jobs. Some programs can be written in a way that they can sort of get their RAM by pooling the RAM of multiple computers. These are MPI jobs. Those require much fancier allocation and setup and coding and stuff. And that's a totally different parallel environment. We're just using what's called the shared environment, which is simple. It means that we want all of our cores in the same node. That's very easy to do and doesn't require any mess, because as soon as you're on a node, all of your cores are right there. You don't have to like be told like the scattered business of, oh, you've got 5 slots in this core and 3 on this one and 2 on this one and whatever. So these parallel environments are sort of like shared as like a really simple, stupid one, but like the MPI ones are a lot fancier and stuff. And so you can get like error messages from that layer of the queue system. And that's why we have these PEs and POs, sort of like the error messages from that layer go there. You will probably always find those files empty and there's just never anything interesting. Our script didn't print anything to standard output or standard error either. So our E's and O's are also empty files, but this is where you would look for error messages and stuff. So like, let's intentionally screw one up. Okay, so like, let's take this script here, the one we're running here in the job, and let's, there's a mistake. That's a command that doesn't exist. So I just used the VI editor to do that, but you have to edit the file however you like. So anyway, now we have a broken script. Okay, so that script's not going to work. So I'm going to submit the same job again. Okay, so this time I'll bother to delete the text files, right? So let's make sure we're going to delete the right things. Is that good? Yeah, that's a good pattern. Okay, so I'll delete these log files. These are all empty anyway, so there's nothing we're losing here. So okay, so now we're back to the way we are, but our script is broken. So I'm gonna run the same qsub command that we've already done. Okay, so and qstat-u, your username, is a synonym for my jobs. Qstat's really the command that my jobs runs. Qstat with no arguments actually gives you the entire queue. It's gigantic. So like I'm going to pipe it to less, and you'll see here that like, here's the guy with the job that's got 256 slots, and whatever. These are all run. You see that R column, right? These are all running. The R's are all at the front. You see all the usernames there too. Different people running things. You see what their job names are too. Like here, this column's the job names. Haven't found the waiting ones yet. Oh, there's the boundary. Okay, so what line number are we at? 30. We're almost at line 3,700. So there's like 3,700 jobs running right this moment. But then there's more waiting, right? So now I'm looking at the QWs. These are waiting. The H is a hold, some kind of administrative hold. That could be one of the queue administrators did it or the guy did it. That's on hold. Queued waiting, but not eligible for starting. QW is just regular queued waiting, eligible for starting. So anyway, so now these are all the ones that are waiting. Meaning the scheduler has to think about where it's going to put all these, right? It's planning for the future. So how's it's about 7,300 lines right now. So the queue manager, the queue system is currently keeping track of about 3,500 running and 3,500 not waiting, and it's got to think about where it's putting all these. Okay, by now it should have run. So yeah, it's gone. I just got my QRSH running. Let's see. Well, now you see. Oh, I guess this will be true. The shell doesn't stop when it has an error, right? It just goes on to the next line, right? So yeah, that actually opens up a little topic we can talk about. But that's why I still have the output file, because if you look at the mistake I made, all I did was insert a new line that's going to be a problem, but that's just going to give you an error message and the shell will keep going. And so this line I actually didn't break and it's still okay. And that's why we still got our output file okay. I could have like changed some letters in here or something and broken our actual pipeline and screwed that up. But instead, I just added a line here. But do you see now in our standard error, it's not like 0 anymore. So now if we look at this guy, you see here, that's a message from the shell that says, on line 4 of the script, this command was not found. This is not really something I really worry about for this workshop, maybe more like in workshop 36. But like, suppose you actually wanted so that like, if this command fails, don't run this command. Like, because I told you the default now is like the shell just runs all the lines. And if one of them has a problem, it just goes to the next line. Suppose you actually wanted to like, if this line fails, do not continue, right? So you can actually do that with this. So like semicolon separates multiple commands in a line. Semicolon also left to right, even if the leftmost command dies, whatever, you just always go to the right. Another option is and. And what that means is only do the right-hand side if the left-hand side succeeds. So this now would only run the big pipeline if this crazy thing succeeds, which it won't. So in this case, we would have gotten the error message, but then the shell wouldn't have even tried this because the and is like semicolon, but it has the extra requirement that if the first part failed, do not start the second part. Whereas semicolon just says, no matter what happened, you just do the parts in order. Same thing as if they were on separate lines. So anyway, but that's like this. That's like gets into error handling, which is sort of like really an advanced topic because it's so messy and difficult. And don't worry about it. But you see how it comes out. So we see it in the standard error log file that we get out of the system. Well, that's pretty good. The only question is now is that I would like 6 of these jobs and not 1, right? Well, let me unbreak this, right? We've already kind of gotten our mileage out of. Oh, I did that without even thinking. Okay, so I put the script back to the way it was. Okay, so that's back to a functioning script now. How do we do 6 jobs and not 1 job? So let me clean up so that we can verify that when we run 6, we're really going to get all 6. So I'm going to delete the output files again. We're back to the way it started. It's actually pretty simple or stupid depending on how you think of it. We just do Q sub in a loop, and we just call Q sub once for everything. We know how to do shell loops. We know how to do 1 Q sub, so we just do a loop of Q subs. So that's all we do. So here, this is fancier than you even need to be. Let's do it even simpler than that first. Then we can look at the one on the slide. So maybe if I look at my history, where's the last time we submitted this job? Okay, so here's basically the way we submitted one copy of this thing, right? So how are we going to run this multiple times? First, what is the file names that we're going to want to run this on? That's these 6 is the ones we want to run on. So we just started a shell loop with that. So for x in srx start fastq.gz do. Okay. Well, now we just do the Q sub, but we have the variable x now that says the file name. So now we just plug that in the right place. So I'm just going to copy my pipeline thing. For this first time, I'm just going to leave all the job names the same. It is not required that job names be unique. Sometimes it's nicer if they are, but it's also okay if they aren't. So I'm just not even going to worry that they're all 6 of them are going to have the same job name. That's fine. This is our resource requirements. Those are okay. Leave that alone. Then there's the script you want to run. That's here. then the argument to the script is the file you want to run. Well, that's now just X, right? That's whatever it is in the loop. And that's it. Done. My job. So now we've got 6 entries waiting in the queue. That loop could have added 100 jobs. That loop could not have added 1,000 jobs. That is what Workshop 36 is about, because you guys have limits like I have limits. So we'll let those think. You know, I don't know if they might already be done, actually. Let's see. Yeah, they're actually already done. So you see now we have a lot more log files because we got an EOPEPO set for every one of those, and we had 6 of those. But you see our output files are here. We can look at those and inspect them that they look good. We can do that. less_star.txt. I don't think I've done less with multiple arguments before with you guys. So that's actually less with a multiple files. When you do that, less will start by showing you the first file. Now the question is, how do I go to the next file? Because if you do Q to quit, it's like done. How do you go to the next file? It's actually :n for next, :n next file. You see the line at the bottom gives you a hint what file you're looking at. And in fact, if you're in the middle of something and you kind of like, what file is this and where am I in it? The equal sign will tell you all about where you are right now. It says you are looking at this file. It's file 1 of 6 on the command line. You are looking at lines 8 to 51. Your screen is showing lines 8 to 51 of this file, and the bottom of your screen is 98% of the way through this file. That gives you an idea of how much more is to go. That's a little bit about using less with multiple files. Okay, so our output files look good. Our log files, you can just tell from the ls-l, they're all empty. Or you could do cat .star, they're all empty, right? There's nothing to show. Of course, one of the things you need to do when you run a lot of jobs is inspect the output. You need to make sure that things work, did all the jobs complete? The outputs look good, whatever. You need to inspect them because things can, even if sort of, and another tip is, before you kick off, if you write a new script and you're going to run it on 100 things, do not do your for loop and submit all 100 the first time. Submit the first part and make sure that works and get that part working, then submit the whole thing. Because otherwise you have a mess, right? Because otherwise you've got, especially if anyway, it's a mess. To tell you how to clean up a mess, the only command that's easy to tell you right now is qdel. And what you do is you give the job number. So I don't have any jobs right now besides my QRSH, but you give the job number, right? Like you saw how each of those six guys that we submitted had their own job ID. If I go back far enough, yeah. So you see, like they each have their own job ID. Qdel, qdelete, and you give the job ID or multiple job IDs, and it'll delete those out of the queue. If it's waiting, they just disappear. If they're running, the processes get killed, and then they're not in the queue anymore. But you don't really want to have to clean up a big mess. So if things are going wrong and you have 100 entries, you have a qdel that's either very painful to type by hand, or you're going to actually have to write yourself some kind of script to help you write the qdel. So the solution is don't run big sets of jobs until you know that individual parts are working correctly. That's just a tip. What was I going to say? So I was going to do something else, but then these finished and we were able to talk about them right away. But what was the other thing I was going to tell you about that? Okay, we could talk about, this. Oh, my resources. Yeah, okay, I was talking about, so why doesn't that work with 1,000 jobs? Okay, I said it could work for 100 or 200, but not 1,000. So type my resources. This is a special command, and it's going to think for a bit. Okay. This is looking you up in the queue system and finding all the limits that apply to you. So it says, I am in MCDB and MCDB2. These are resource groups in the queue system. We have bought nodes and contributed them to Hoffman. So I have special access to these particular nodes. They're in what are called my high P group. I think, for example, in the general cluster, you only have a 24-hour max, like your queue, your individual jobs max out at 24 hours. In high P, like I think it's 7 days. You can request a node for up to 7 days. You can also request exclusive access to nodes in high P, meaning you can ask for a completely clean machine, meaning you are the only person on that machine. You have all of its RAM and all of its CPU, and do whatever you want for your up to 7 day time limit. So depending on what group you're in and so on, whether you've purchased nodes and so on, you may have nodes here, you may not. This is just telling me that I have high P access to the following resources. It's just what this is telling me. It's these nodes, and these nodes have the following attributes, like how many cores, how much memory is in these guys. You see, we have one of these is like a 256 gig RAM machine. Some of these are 192 gig RAM machines with 36 cores, whatever. And then there's these limits sections. So this says that in certain queues, I have a limit to 72 slots, 92 slots, or 100 slots. So this is now the most number of slots I can have active at the same time in these particular sub queues. But then the limits I want to talk about are down here. And this says the maximum number of jobs you can have in the system simultaneously, 500. So the type of jobs we are currently submitting, each one of those counts as one. So this is saying you can have 500 entries in that queue. So this is what I'm saying. You can't do a for loop and stick in 1,000. Well, maybe you could if you were so slow, if you slowed the for loop down so slow that they were finishing faster than you were putting them in or whatever, right? But you can only have 500 entries in that my jobs list at a time. So then how do you deal with jobs that are really big? The answer is there's another system called job arrays, which allow you to essentially collect huge numbers of related jobs, like the same script against a whole ton of files, and only use one entry in the queue slot, but it'll sort of like auto-generate all the sub jobs inside of it. These are called array jobs. That's what we talk about in workshop 36. And you can see here that my per array job, I can have 75,000 tasks. So I could have 500 array jobs, each of 75,000 tasks, and that's a lot of tasks. But to do the huge numbers of parts, you have to use arrays, which we're not going to have time to talk about. But you do get 500. Do you guys have 500? Are you the same as me? Yeah, 500. Okay, so yeah, so that's pretty big. I mean, whatever. I mean, that's so I'll call that like small to medium sized problems. This is now kind of the array jobs you only really need for sort of large size problems, but you can do a lot of work with this 500 size slide. Yeah. They wouldn't all be able to kick off simultaneously, probably. But it also depends. So like, I don't know if these queues cover everything. We might have access to some queues that aren't limited. It's just saying that in these particular queues, your total slots limit is this. I actually don't think these cover everything. So like, and I've certainly had more than 100 slots in flight at a time. So it's just, because it's like different parts of the cluster are contributed by different people and stuff and whatever. So it's sort of like, these are all just like rules to sort of make like the people that own things have more freedom than the people. If you bought this huge piece of Hoffman, then you get extra access to that piece, of course. But so these rules are just kind of things like that. So yeah, so it really depends though. So like I would recommend, to the extent possible, you really aim for your parts to be small. So like, what does that mean? I would say under 2 hours apart, but you can't really predict exactly how long a part is going to run. You don't want to do some test experiments and like kind of like scale your parts to like be an hour, 45 minutes, because it's just too close to the edge. And with random fluctuation, you might go over the edge and stuff. So I might say aim for like 45 minutes or an hour for a part, but ask for 2 hours. That'll handle most of the variation. You might get some weird outlier where a machine is really bogged down and it should take like an hour, but because it's bogged down, it's going to take 3 hours or something. And so that part dies because of the time limit. But if you kind of aim for like around an hour, but ask for 2 hours, probably most of your jobs will do okay. Assuming you've done your kind of experimentation on the small, before you go to the full scale, and you kind of reliably know that your parts are going to be about an hour on average. And yeah, it's still extra 2 hours. So yeah, so I would say like kind of aim for an hour, ask for 2 hours. 1, 2, 3, 4, 5 cores. RAM kind of scales per core. You could aim low, like 2, 3 gigabytes a core, or you could actually kind of go up to like 6 gigabytes a core, and that would still be a big fraction of the cluster. But kind of like if you do like half-hour jobs, like 1 core, 3 gigs of RAM, you could get a lot of those running at the same time because it's so easy to fill holes in the schedule with it. And I've had 300 of those running at the same time. But as you ask for more resources, it's harder to place. You're going to have just less of them open at any given moment. You'll have just less running at the same time. So it's kind of hard. You have to really experiment to kind of like find like the peak of the performance curve. If your goal is like shortest time from kickoff jobs to minimize the time from kickoff of all jobs to last finish of the last running part, that wall clock time, that's most usually what people want to minimize. You have to kind of play around, kind of optimize the speed of the thing going on. Yeah. Yeah, we're not going to talk about Java rates.
Yes, but sorry, my question is not about Java rates, but it's about like this
Yeah, but you're going to have a fairly small fraction of the cluster that's going to be qualified for running those, because there are many nodes of Hopin that do not have 30 cores. Even if the node was completely empty, which it also is not going to be generally true, it's not going to be able to place your job on that machine. So yeah, this is why, there are nodes with 30 cores. It's not impossible to satisfy, but you're restricting yourself to a subset of Hopin. And those nodes are going to have to be fairly empty to qualify. So you're going to be waiting quite a while for those to start. And you're not going to have the amount you're simultaneously going to have running is just not going to be that big because there just aren't that many in the cluster. Whereas it's better to kind of always cut into smaller pieces because they're just, you know what I mean? It's just like, just because the pieces are smaller and there's more of them doesn't mean that that's going to be slower or the same speed as fewer bigger jobs. In fact, it'll probably be faster because it can be shoveled into the schedule so much easier. So yeah, so I kind of really recommend making parts small and not big. On the other hand, you don't want parts that take like 30 seconds. It's too small. It's like then you have too many parts. There's too much overhead in the getting jobs in there and starting jobs and so on. You want jobs that run for tens of minutes, up to an hour or something, because then you can ask for 2 hours. There's sort of a threshold, I think, at 2 hours where sort of like jobs under 2 hours get kind of like a priority boost. I think the boundaries are 2 hours and 24 hours. 24 hours is a hard boundary. Beyond that, only high P is qualified. But like under 2 hours are kind of like extra fluid, and the system likes those. The 2 hours to 24 hours are just kind of like medium priority. Yeah, anyway, that's my recommendation just from using Hopin for a long time. Yeah. Well, how do you ask for high P? Yeah, so the resource usage line here. So like the yellow stuff here, and then so like there's the PE stuff, but then there's the L. The L is all about the resource requirements. So you just put in here high P. If you read the cluster document, I think like way on day one, like the first slide or something, or second slide, or third slide, yeah, whatever. Exactly. Here, this slide, this cluster documentation link. This is like all this stuff is talked about there, like high P and all this business and whatever. It's all talked about in these documentation pages. Okay. All right, so we're just cleaning up miscellaneous topics now. So like, okay, so here here's one, the resource requirements though are like one of the most annoying parts of the whole system, right? Because like, how do you guess? Like, well, cores you sometimes kind of know because it's like, how many things am I running in parallel at a time? How many programs am I running in parallel at a time? Or some tools like SAM tools sort explicitly take a command line parameter where you tell it how many cores you want it to use. So like counting the number of cores that your pipeline is going to need or something, you can kind of do rationally already. Time you can also kind of figure out. Maybe like before you've ever run it once, it's hard to guess the time. But if you kind of cut your data down to smaller, or you already have parts or something, you can run some parts as an experiment, and you can empirically figure out kind of how much time you need, right? So you can kind of get a handle on the cores and the time problem. But the worst one is the memory. Like how do you guess that, right? It's just like random number. Well, there's several strategies. So one is you just kind of like run some experiments and you keep decreasing it until things break. And then you go up a little bit from there. So like you try like 20 gigs of RAM, 10 gigs of RAM, 5, 3, 2 breaks. Maybe go to 4. You want some margin just for the same reason why you kind of want to aim for 1 hour, but give it 2 hours. You don't want to cut the memory too close either. So if you find out that like 2 is iffy, 4 probably works most of the time, give it the 4 or something, right? Another way to do it is to ask the queue system what your interactive session needed. So you can go backward in time and ask. And to do this, the way it would work is you would start a new interactive session. You would only do the things that your job needs to do in that interactive session. Don't do extraneous other things that will confuse the numbers. And when you start the interactive session, you note the job ID. Then you exit the interactive session. Then you can ask the accounting system, what was the maximum memory usage that interactive session needed? That tells you kind of what your high water mark was in that experiment. Then you can round up some, add a 20% overhead or something, whatever. That gives you some idea of what to ask for your job. So how do you do that? So you can take any job, interactive or a completed job, as long as you know the job ID. So let's find a job ID of something we ran. So here's one of the job IDs that we ran. Then you can say Q accounting, job ID, blah. It'll think for a while because it's got to go dig it out of the log files, which are huge. So these are all sort of like the statistics that were collected at the conclusion of that job. And the important ones for memory, well, like for example, here it'll tell you like submitted, start, and end. That'll tell you the actual time it took rather than you asked for 3 hours or whatever, but there's a record of the actual time that it took. It took like what, 1/10 of a second or something, these were very small that we gave it. But there's numbers down here, like, where did they put it? This might be easier on second example we do where we do some more work. These are just like too small. This RSS number is kind of related to the memory, but the units are funny. It might be kilobytes. This is a kind of too small of a job to kind of really dig into this. But basically, there's one of these line max RSS that's even listed as 0. I think it's actually, it might even be like sampled statistics, so it's only collected like every few seconds or minute or something. So if it's super fast, it may get just a 0 here. This is not a great example. But basically, if you ran a substantial job here, like this maximum RSS, the RSS stands for resident set size, which is basically the RAM that it was using at one moment. You would have a number here like 3.4 G or something. And then that would tell you that was the high water mark for this job. And then, maybe you try submitting jobs with 5G as RAM or something or whatever. So, like I say, so one way to use it in experimental mode would be start an interactive session, note the job ID, do just what you want to collect statistics on, exit QACCT-J, that job ID, look at this line max RS, and that gives you an idea of how much memory you were using. Because the interactive session, you would probably just request a big number, right? Like 20, 30 G or something, right? Because you just want it to work, right? Then you sort of want to do your experiment with a big ceiling, but then find out what was the high limit that I actually used. And that's what guides you to do the job submissions. Okay, so that didn't quite work because this jobs are kind of too simple, too small to produce real numbers there. But we'll do one more example. Maybe we can try again for that. So like I said, the large scale usage, you need to switch to Java arrays, which we're just not covering. Workshop 36. Let's do one more example. Okay, so we need a task to do. Let's do BAM file. So there's a couple of reasons I want to do this example. One of which is that it's a reminder that inside your job scripts, you have to set up your environment. However, if your interactive session is doing something and then you do the pipeline that you want to run, but then you want to translate that to a job script, you have to set up the environment the same way. So for example, if you need modules from the module system, like samples and stuff, you got to pull those in. If you want shell functions and stuff, you got to define them over here and so on. So this is an example that includes that as part of it. And also it just kind of is more of like a template for you to kind of plug in pieces to, rather than sort of the one we just did, which is sort of like a really minimal example that doesn't, it's kind of a little too stripped down. So let's see this one. So we're still in the same, we're still in your copy of this, we're still in your scratch space copy of the stuff where we're at. I am going to get rid of the files related to the jobs we've just been running. I'll leave the percentage details, but these log files, which are all empty again, I'll get rid of just because it clouds the listing, makes them longer than they need to be. So, okay, so let's suppose that you've done alignments with, you've got reads, you align them to a reference genome, you got a BAM file, and now you're interested in filtering to unique reads, because maybe you want to do an analysis and you kind of want to define unique reads and analyze unique reads. So there's multiple ways you can attack that problem, but one way is that most aligners fill out column 5 of the SAM file. If you uncompress the BAM file with SAM tools, you get the SAM version, which is that multi-column big text file that you saw. Column 5 of that SAM file is called MapQ, mapping quality. And it is a logarithmic scale. It's a Fred scale thing. So like 10 means that there's a 90% chance sure that the aligner is 90% sure it's in the right place. 20 means it's a 99% sure it's in the right place. 30 means it's 99.9% sure it's in the right place. 0 means it's totally not sure where it is. Multiple hits should really be in the 0 MapQ, or maybe 1 or 2 is probably 0. Anyway, so, but other things can just MapQ, like the quality of the bases and the reads and stuff. Anyway, the MapQ is basically the aligner's expression of how unique the alignment was. So if you want to turn that into a decision about like unique reads, maybe that means you're putting a threshold on MapQ, right? So you're going to call a unique read. Your operational definition of unique reads will be the alignments where MapQ is greater than or equal to something. And the question is, what do you choose the something to be? And so one of the ways that would help you to choose the something would be that if you knew the histogram of MapQ across your file, that would help, right? Because you're kind of interested in how many alignments would be surviving if I as I vary the threshold, how many alignments do I survive, right? Like I wouldn't want to choose a threshold where like 90% of my data disappears or something. Right? You kind of want to know what that curve looks like, because as I vary the threshold, how much of my alignments do I keep? So, for example, per sample, we would like a histogram of the map column. That would aid us in making decisions. So we know enough to do that now, right? So like, okay, we got to build out our pipeline. We need some BAM files. So let's see here. Here, I think this is the directory which is going to have some BAM files. Okay, so we're going to make this shell variable indir. That is a directory that's holding some MapQ file, some BAM files. So if we look inside that directory, there's some BAM files, and we'll use these as a demo. So I'll make a variable BAM that just has one of these so that we can build our pipeline with one of these as an example. So that's indir / and then we'll just pick one of these, the first one. So, okay, so BAM is a shell variable that's pointing to some random BAM file. It doesn't really matter what the BAM file is. We just need to build our column 5 histogrammer pipeline. Okay, so we're going to need SAM tools. Is SAM tools loaded right now? No, it's not for me. So I got to do a module load SAM tools version 1.15 is the one we've been using. And then we're not going to need the header line, so we don't need to give any arguments to SAM tools view. And then we just can give it the BAM file and type that to less, and that's the SAM file basically, right? So this is the read name, this is flags, this is chromosome position, map Q is here. This is the fifth column, 1, 2, 3, 4, 5. So now we pull out, we know this is a tab separated file from earlier today. So we pull out column 5, just to convince you it's not all 0. It's like some of these, it does vary in this file. That is what we want a histogram, but we know how to do integer histograms, right? If there's one thing we're good at now, it's that. So, you know, maybe we're going to need some buffer size there we could choose because, you know, this is going to be a fairly big, thing. So, you know, whatever makes sense. We get to choose when we submit the job how much RAM we want. So we'll just, I don't know, we'll pick 5G or something, whatever. Anyway, so, and then we want the temporary files, if there are any, to be written to the current directory instead of depending scratch space. And why don't we sort this numerically? Because we'd like the final histogram to be in increasing map to order. For the same reason when we did the %CG content histogram, it was nicer to keep the lines ordered by the %CG, because then that's the same way you apply it. So the same situation here, we will sort these into numerical order. Then we will pipe to unique-C. That'll basically give us the histogram, but now we got the spaces for them, and the column 1 is the tally, and column 2 is the long day here. Here, we should probably test this at some point, right? So that's a big file. Let's cut it down to like 1,000 lines so that it doesn't take too long and see where we're at. Okay, so let's see if this is working. Yeah, okay, that's working. That's just the first 1,000 lines of a demo file, but that's enough to kind of see the pipeline is currently syntactically correct and functionally correct. So now we just want to transform to the 2-column tab separated format. Okay. Boom. That's good. That's our histogram that we want. Then we would save that in a file, right? So now then we put this in some output file. And we will construct the output file name from the input file name using the same trick that we just did the last example. But that's basically it. So that's now basically the meat of the pipeline, and then we just flush it around with the stuff that we just did in the last example. So that's on this slide. So here is, in fact, the script is here, right? So that's this third script file that's here, histo map q of BAM. So let's look inside that file. So it's got a shebang line, as it must to be a shell script. Then there's some comments in here. These things that start with a hash mark are just comments. But sort of like this is to give you sort of the general idea of like sort of like the template that you should follow when you make new ones of these. So the first thing that I recommend doing is sort of renaming all the command line arguments with variables that make sense. Especially because if you ever have to renumber the command line arguments or something, it's just much easier to have them indirected like this. So we have to decide what command line arguments this thing is going to take. Well, certainly one of them has got to be the BAM input file name. We're going to construct the BAM output file name from the input file name. So the output file name doesn't have to be an option, a command line parameter. We could have done that, but we'll just have it make the output file be built off the input file. But there is one more parameter that's kind of relevant, and that is when we kick this job off in the job queue, we'll have to say how much memory it's going to get. And then it would be good to give sort the advice that that's how much memory you're allowed to use. And the easiest way to communicate that information is to just let that come in as another command line parameter. So the first command line parameter will actually be the number of gigabytes of RAM that the sort is allowed to use. And that will be related to the parameters that we put into QSub and ask from the QSub. Then the second command line parameter, we could have chosen this in the other order, but it doesn't matter. But the second command line parameter will be the BAM file input. Okay, so then I recommend that all of your scripts start by doing an echo that just says I'm starting, and another one at the end that says I'm done. Because that way, when you look at the log messages, you can tell whether the script actually hit the bottom or not. And what kinds of things do you log? $0 is actually the name of the script. That's the 0th parameter. It's kind of the command position. $@, as you saw before, is all the parameters. So I could have just said like $sort MGB, $bam, or $1, $2, but it might as well just say $at and get all of them and not have to change this as the script changes in another situation. I meant to talk about these before. We've seen them a couple times actually, and you've probably figured out how they work before, but this is actually another form of substitution that we haven't really talked about, I think, in like explicitly yet. So this is called process substitution. And when you have $ in parens, you then can put a whole shell pipeline in there. And then whatever comes out of standard output, that is what the expansion of this is. So this is like a fancy shell text expansion. It says, treat this as a shell command, go and run it, collect what comes out of standard output, and that is what this $ thing expands into as text. So this echo command will actually get like the output of date embedded into this string, and this is the host name as well. So these will be run as commands. The standard output that they produce will just be plugged into here as the expansion. So if we like run this, you'll see that produces output like this. Okay, if you talk to people that are used to really old shell style, another form that's done is with backticks. So sometimes you'll see, just for education in terms of reading other people's scripts, you may see that done with backticks like this. That on my keyboard, the tilde and forward quote is this way. These are back quotes. Do you see the difference on the screen? It's slightly different. It's a different key on your keyboard. For me, it's the one that's next to tilde. And it's usually called back quote, or for programmers always love shorter names. So backtick is usually easy to say. So people say backtick. I just don't use that form. You may see scripts other people write in that form, and it's an archaic form. It works when it works, but it doesn't work in more. It has more problems than the parenthesized form does. The parenthesized form, for example, nests. The back quote form is really nasty to nest, and it's just you'll have less problems when you use the $paren form. But if you read other people's scripts, you may see this back quote stuff. Yeah, so this is just logging. This blue stuff is just logging. I guess I'll do it. It's the same as on the screen, but I'll do it in the slide because the slide is colored, so it's easy to talk about like blue stuff and so on. So the blue stuff is logging. The yellow stuff is to set up the environment. So actually, I chose to do this. I did this here by not using a shell function because the histogram stuff we're so comfortable with now, we can just knock that out and so on. But like basically this part is to prepare the input to the histogram. This is the histogram part here. And we did earlier, maybe that was the second day, we did a shell function that does histograms. And just to show you like what it would look like in one of these work scripts to have a shell function inside of it, here I decided to do the real pipeline using the histogram part as a function. It's probably too simple of a case to actually really do it this way, but I just want to show you what it would look like to have a shell function inside one of these scripts. So this yellow stuff has two jobs. One is to get this shell function defined that the actual pipeline in red is going to use. The other part is that we use samtools. And samtools, as you know, is not part of Hoffman's default. If I start a new session in Hoffman and I ask for samtools, it's not going to be there. So that is something that when our job starts in a fresh environment, he's not going to have samtools. So we have to make samtools be available inside the script, just as if we were sitting interactively. And so that is why I have this module load samtools command here. Now, the only trick is that the Hoffman people didn't have to do it this way, but for some reason they did do it this way. And shells that start up inside job scripts get slightly different startup scripts than the ones that start interactive sessions and login sessions. And so the module command is available in an interactive session. Like right away, I can say module. I don't have to do anything to make module be available. But for job scripts, they don't see module naturally. So just treat this line source -rc as some magic. This makes the next line uses the module command. This makes module be available inside your script. Okay. So, but basically all this yellow stuff does is to try to get all your environment set up. So you got to get your module set up. You got to get your function set up. If you have more shell variables, whatever, you got to get your environment set up. That's the yellow part. The red part here is the actual meat. So the actual meat is just SAMTools view. We have, so back in the orange part, we captured the BAM file that's to be input in the variable BAM. Okay. And so we do SAMTools view BAM because I actually chose the same variable, I think, in the interactive prep to this. So that's okay. And then we pipe that to cut-F5 to get out the map queue column. But here I'm using the function that is the histogram part just to show you what it would look like, right? So that just takes the place of all the stuff that's highlighted here or whatever. But we've seen basically this function before from day 2. Now the only thing different between what we played with here with the less to see the output is to actually write the output to a file. So here I'm writing it to shell variable out, whatever file name that is. The reason is because these 2 lines do the business of constructing the output file name from the input file name. But let me talk about that a little bit. So one thing is that here the input file name is actually going to be in a different directory than where we're sitting. So we have some decisions to make. So like, what was the path to the BAMs that we're going to use as input are not in this directory, right? The path is something like this, right? This is the path where the BAM is, and it's in a different place than we are now. We have a decision to make. Do we want the output histogram to be written where the source is, parallel to the source over wherever that is next to him? Or do we want the output to be here where we are now and where the script is, right? That's a decision to make. I would generally recommend that you leave the inputs wherever they are, but you sort of, the work that produces the new outputs, you just put the output, like the output would go here, right? So it's kind of like, because if you're going to do a whole series of steps, you just sort of like let each step generate its output sort of where it is. And then you make a new directory for the next step. And you use as the input steps, you back up and pull out files from over here. But you let this new stage write its output files in this directory, right? So then you can keep going like that. Otherwise, you're kind of going to mix stages in the same directory and stuff. It's more confusing and stuff. So I'm going to say, even though our inputs are someplace else, let's make the outputs where the script is and not where the input is. So that gives us a problem that we haven't had to solve before, which is if you're given a complicated path name, how do I get rid of all the directory stuff? Because if I want to create an output file that's something like here, so the output file name is going to be something like this, right? It's going to be like histo mapq tally.txt or something like this, right? But I don't want all this stuff on the front, because if I keep this stuff on the front, it's going to put the output file over there, right? So I need a way to delete all the directory business at the front of the path that's the input path. There's 2 ways to do it. One is to use this command called base name. And if you do base name and give it a command line argument, it does exactly that. It strips away all of the leading part. The opposite of base name is dir name, which is the directory name, and it gives you, oh, you need a space there. I don't have a space there. That gives you only the directory part. But that kind of those 2 kind of take it apart. So basically, one way to do it is this. So what did I just do? I just assigned, I had to use the process substitution to do this because base name is a whole command that produces output to standard output. So we call base name to BAM, that spits out the thing we want, which is just the file name part. And then I captured that in a new shell variable. So that is now a new shell variable that has just what I want. And now I can take that and add my, well, actually, we know how to strip out a suffix, right? So the %.bam will kill the .bam at the end. We already saw the % trick just earlier today. And now I can do the .histo mapq tally.txt. And that's now the path that I want to produce as an output file. Another way to do it is that the shell itself has enough text substitution to do that kind of thing without using base names. So I think I didn't mention it, although it was kind of a comment in one of the slides earlier. There's a little blob of orange text here that kind of tells you what some of the fancier text substitution you can do is. And one of them you can do is to, what slide are we on this slide? So just like % deletes suffixes, # deletes prefixes. What you also probably don't know is that the prefixes and suffixes can be patterns just like file names have patterns. So if I do delete the prefix // that will delete anything up to a slash. The next thing is that with a single pound sign, it only does the shortest match. We actually want the longest match. So we have to do 2 pound signs. So that says the asterisk means anything, but basically what this now means is delete the longest prefix that ends in a slash. But that's exactly what we want. That gets rid of all the directory stuff. So that's also the same thing as the base name trick. So that's what you see in red here. That's these extra 2 lines are to do the transformation of the input file name with all the directory stuff on the front, kill the directory stuff on the front, kill the .bam on the end, then add the .histo blah blah .txt suffix, and that's the output file name. And so that's how that works. So like, yeah. So since our BAM variable is currently set to the right thing, yeah, it's it's something one of the BAM files with all this directory stuff. If we run these 2 lines and then echo out, you'll see that it's built exactly the output file name that we want from that. And so that's why in our real meat pipeline, all we got to do is send it to out, and there we go. The next sophistication, so that's the end of the script, and that's fine. It's ready to go. We should probably test it. We're about out of time here, 4:30. So we don't have time to test it individually. We'll just assume it works and keep going. So here's another trick. So the last time that we did multiple queue submissions, we had a for loop. It was here. Actually, we didn't really talk about the slightly fancier version. The only difference between what we did live and what's on the slide here is that the slide takes care to make the job names all distinct. It just calls them histo 1, 2, 3, 4, 5, 6, and it does that by just setting a variable to 0. And then every time through the loop, it increases the variable by 1. And so it just gives the jobs all different names. It's no big deal. But essentially the structure of our loop was a for loop over the file names. And inside there was an explicit call to QSub. So another structure that you may find appealing is to instead encapsulate the QSub in a shell function. That way, when you can just sort of give the command submit one and a file name and kick off one anytime you like. So that's what we're doing here. So we're making a function called submit one histo map q of BAM. It takes 1 command line argument, which is the BAM file to do, and it queues it as a job. And so this is something now that's easy to just do one-offs on the command line if you want to do one-offs, or just put a little for loop around that and call that function multiple times. But it kind of, this function hides all the QSub messiness inside here. So you don't have to remember all that QSub stuff. It's all just encapsulated inside. So here I've also taken the trouble to make these shell variables be local variables to this function so they don't leak out outside the function, but that's just a subtlety. This is not really that important. But basically that's just to avoid disturbing the environment outside this function. There's no need to let these parameters leak outside this function, so we just declare them local. Maybe just 2 cores, 4 gig of RAM per core, half an hour. The total amount of memory in the job then would be the product of those 2. But maybe, like I was telling you, you don't really want to run the line too close. So then maybe we'll tell sort you can use 1 gig less than that. So then we back off by -1 there. And so then we just do a little progress message. We're submitting this guy right now, and we do the QSub command. We don't bother to name the jobs distinguished here. We just call them all the same. That's fine. And we just plug in all of our shell variables here. And here we call our new shell script. That's the script over to the left here. And remember, command line parameter 1 is how much memory the sort should use. And that's, we just calculated here. And then the BAM file, which is the first command line argument and only command line argument for this guy. So we put this function here into our guy. Okay. And now we're ready to go, right? So like I said, we've already got this one variable, which is this guy. And so now we can just call our function anytime we want to kick off one of these, right? No, okay, so submit that guy, so now that's in the queue. Let's see him go, hopefully. Running. And now you see he takes a little longer, so he doesn't just like disappear in a second. This one actually has some work. If I remember right, it's 3, 4, 5 minutes for one of these, I think. you see that we have the logging files have started. We don't have an output file yet. We have the empty output file because as soon as we do the shell redirection, that file will be created. But this is not going to fill up until all the sorts and the histogram stuff is done. So it's going to be a little while before that thing gets populated. If we look at the standard output log already, we should see our script stuff. Oh, did it just finish while we were waiting? Is it really that fast? Looks like it is that fast. Okay, so in between there with the log was 227 bytes. Here the log is 453 bytes. So the second line got added in between those two. So, but anyway, so there's the progress line from the script that I was at the beginning. There's the progress line I was at the end. The rest of the log files are empty. There are no error messages. Here is the map queue tally and the output. And there it is. Looks good. We should do the other guys here. So if we look in the directory where that BAM guy is, there's some more. So that was this directory. So if we look in there for star.bam, we have 6 of them. It's actually the same experiments as these are, but these are like just 1,000 reads, and these haven't been aligned yet. This is like after aligning the whole files. These BAM guys are. So why don't we just submit them all? Okay, so we'll rerun the one we just did because it's a pain to just figure out the 5 rather than just run the 6 again. So okay, so all we're going to do is do a quick little loop here for X in whatever directory that is. This directory. Well, this is the file name pattern anyway. So that's the file name pattern that expands to 6. Then there's the name of our submit function, whatever we called that. That's this. Submit. Done. There they are. Well, we kicked off 4 of 6, but somehow not 6 of 6. Oh, we got 6 of 6. Yes, but because of the 500 entry limit, you're going to have to paste that so that you don't ever exceed 500 in there at the same time. Okay. We got one left, one straggler. There we go. Okay, so there they are. All of them are empty except for these guys, but these guys should all have 2 lines each. Okay, start and start and start and start and start and start and they're all there. And let's look at those tallies. It looks good. We could do less on all of them. Okay, 1, 2, 3, 4, 5, 6. Okay. We probably want to visualize them. This is no longer a job really for command line stuff, but the data has been collected. This is now something you would import into R or whatever your Excel or whatever you want to graph this thing in, just to show you like one way to do it in R is on this slide. And I actually this was also an excuse to show you another thing that like most languages actually have pipes. And if you have the SSH command with passwordless login, so like one thing you may not know is that SSH takes an argument. I mean, you know it takes an argument because it takes your username at the machine. Did I spell it right? Yeah, okay. But if you continue and add more arguments, it will run this as a command and then quit. So if I do cat and then a path to some file, like my tally, one of these that I just made. So that is the full path on Hoffman to where that thing is. So in R, because R supports pipes, the command is really long, so I have to use paste 0. I mean, I don't expect you to know R here or whatever, but this is just a paste 0 is string concatenation in R. It's just what you do if the string is really long and you can't fit it in one line. So I basically build a shell command, SSH, blah, 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 you know, crocus at cat and one of these files that we just made and wrap our pipe around it. And then you that gives you something you can actually pass to R functions like read.table, which is probably, if you've used R, you've used read.table. So you know that read.table can read files on your local machine. You probably didn't know that read.table can read from pipes on your local machine. But basically what this kind of does is that it means that when I run this R code, my R code is going to pull from Hoffman live that file, right? I don't have to like transfer it to my machine and have it be a file on my local machine. I'm pulling the live copy out of Hoffman with my little SSH trick in that pipe here and stuff. So yeah, and then we're just gonna, here we do it cumulatively because we're thinking about this. We did the histogram where each row is like, if the map queue is 47, this is how many alignments there are. But in terms of doing it as the problem that I introduced, which is like, I'm thinking about making the threshold 47. In that case, what we should plot is not the number of alignments that are equal to 47, but the number of alignments that are greater than equal to 47, because those are the ones I would be keeping, right? So we need to switch in R from the raw data that we collected to the cumulative from the right version. And this little XY business mess here, this is all about transforming. The X is the map queue, the Y, we have to reverse the order cumulative summit and then reverse it back again. That's cumulative summing from the right. And then we can do a plot and whatever. And anyway, this is how you can do multi-panel plots in R. Anyway, you don't have, we're not about R here, but the point is that with that little R code there, oh, did I get the path names wrong? So that's not going to work because the path names aren't right. What's wrong with the path names? Kind of looks okay, but like there's got to be something in this path that's not right. So U scratch C focus workshop 1B, small examples, SRX 112HS 21 NT 111 centimeters 108 sorted histo. Does anyone see what's the difference? Oh, there's another directory. Right. Okay, so yeah, you're right. So that's what's wrong. Okay, so this is this directory shouldn't be here. That's not where we did it live. Thank you. And working. It's working. There it is. There's our figure. So this maybe isn't the super ideal way to do this. Maybe you'd want to overlay all 6 plots with different colors so you could compare the lines easier than this, but whatever, this isn't our focus. And you can see there's some difference between the samples. Like this sample is a little qualitatively different than kind of it doesn't matter. The point was to kind of show you just the workflow and not the details of the analysis. So anyway, we're out of time. So if you're interested, here's just some more stuff to follow up on. As I say, workshop 36 is where we get into the array jobs and the scaled up version of analyses and stuff. Like, how would I take a huge FASTQ file, break it into parts, align the parts, reassemble the alignment again, and stuff like that, and run thousands of jobs in the middle, and so on. So that we talked about that in the report. So anyway, thanks for coming these 3 days. Hopefully this was helpful. And maybe we'll see you at another workshop. Let me stop the recording.